All right, so part 2 is going to be a continuation of part 1, and it's just going to give you an overall understanding of like why we're covering what we're covering, like I was saying. So right here, if we're talking about the positive side of the circuit, that's what do we say that is? The positive side of the circuit's the power side. So if you say, oh yeah, it's a power side switch, that means that the switch is on the positive side. Whereas if we said it's a ground side switch, that's on the negative side, right? So if you essentially split your circuit in half, typically on the wiring diagram, so you know, the power side is usually on the top. And then it usually flows down to the thing that does the work, which is the load. And then typically after the load is downward, and it becomes the ground side, the negative side. And that goes to the chassis ground. But not always, and sometimes wiring diagrams can get very confusing, and there's so much stuff they have to fit on one page that sometimes the positive comes from the bottom and the ground is at the top. But generally, we like it to be positive on the top and negative on the bottom, at least ideally. All right, and then like I was saying, if you see the supply side and you're like, the supply side, again, that's the positive side. So if you see power, positive, supply, source, that's all positive stuff. Then if you see ground, negative, chassis, common, that's all ground. That's all negative stuff. And the wire colors, generically, probably the positive is going to be red. Probably the negative is going to be black. But sometimes the positive is yellow. And sometimes the negative is black and white, or white with black. And so, or sometimes the negative, the ground could be green too. Depends on exactly what you're working on. So the wire colors are a good, like an indication. Like if you rolled up to a battery and you saw a red cable and a black cable, you know what those are, right? That's pretty consistent. But if you're working on a headlight, the positive could be red, but it could be yellow. It could be blue. It could be blue with a white stripe. It could be any number of colors. And then the ground could be black, or it could be black with white, or it could be green. But at least if you keep these in your mind, you're kind of like, I think I know what those wires may be. But if you really need to know, you need to pull the wiring diagram, and you need to look at the diagram, and you need to see what's the power side and what's the ground side. So that way when you go to test it, you know what you should have. Makes sense? So this is just like a general what the wire colors may be. Okay? And then, in fact, I want to explain one more thing. Where do you think the fuse is going to be? The fuse. True, but on the power side. Yeah, exactly. We don't fuse on the ground side. So, like typically, if you have an issue with the fuse, you know, we're checking all on the positive side, on the power side. So it comes from the positive battery, then it goes to the fuse box, then the fuse box has the fuses in it, leaves the fuse box and goes to the loads. And after the fuse box, it's probably where it's going to change color. Going to the fuse box will most likely be red. Okay. And like I was saying, the ground. And so let's just cover for a moment the chassis. You know, so if you guys want to call it chassis, you can, but that's not how it's actually pronounced. So the chassis is the ground side, right? Here's a really good diagram showing you the chassis. So if you look, we've seen this before, but the red, where do you think the red goes based on what I just told you? Because it's got to power a whole bunch of stuff. Everything in the car that's run electrically comes from the positive terminal. Do you think every bulb and every component's going to be connected here? No. Eventually, I mean, in a way, yes, but not directly. So we're going to pull the positive off and send it to the fuse box, and then it'll probably branch a couple other spots too. That'll probably go directly to the starter. The starter typically doesn't go through the fuse box because the starter is like such a huge cable. It draws so many amps. We don't actually fuse that one. It's just, it's like, how would you have a fuse that big? It goes around it. Yeah, it just goes direct, boom. So a lot of times this positive will actually split off. One will go to right to the starter terminal. And then the other one will go to the fuse box. And then, from there, it'll go everywhere. And so on the positive side, a lot of times we'll call that like the power distribution. So I've seen people get stuck a lot. They're trying to diagnose this concern, and they're like, well, I can't find a diagram for that part because, they don't know what to call it. So if you can't find a diagram and you think it's like right up around here, somewhere between the positive terminal and the fuse box, that's probably called the power distribution. And that's a specific wiring diagram. There'll probably be multiple. It'll show right from the battery. Whereas if you jump in and you're trying to diagnose headlights, if you pull up a headlight diagram, it's not going to show the path all the way back to the battery. It's just going to show you the path from like maybe the fuse box, or sometimes even just from the module, or just the switch down. If you want to see all the way to where it originated, that's the power source diagram. The source of power is like the battery, right? Then the chassis, like I was saying, here's the ground, right? This ground is going to come down, and if you look, it's kind of weird, but it just goes right to the frame right there. And so on the positive side, the fuse box distributes the power to all this stuff, right? On the negative side, you got to consider that's kind of like the return path in a way. On the negative side, it's going to most likely flow through major components. The engine, like the engine block, the transmission, the frame is a big one. All those, because they're all metal, or even the body of the vehicle itself, especially if it's like a car, it's a unibody, so the frame and the body are one unit. If it's on the ground, it's flowing in the metal through these random major components, and ultimately it'll go into something like this, and this will dump it right back into the ground. It's like a fun thing I would do for students, and if your memory's pretty good, I may just spoil my chance to trick you right now, but that's okay. I would take this bolt off, and I would like put a little electrical tape on the bottom, or like a piece of rubber, and I'd bolt it back up, and you'd go to the car, and you'd turn the key, you'd turn the lights, nothing would work. Nothing electrically would work. You'd be like, oh, the battery's dead. And that was a good guess. And you jump it still wouldn't work. And then you'd be like really fixated on like the positive terminal and the fuse box. But see, I would fool students a lot, and I would mess up the main chassis ground. And if you have no ground path back to the battery, you might as well have disconnected the positive terminal. It's going to have the same effect, right? So the positive is just as important as the negative, and the negative is just as important as the positive. And if you have an issue with no power to anything in the whole car, I'd be suspecting this. And that a lot of times has its own wiring diagram, like the ground diagram. They'll just show chassis ground or ground diagrams, and it'll be grounds all over the place. A lot of times redundant, but this one is not redundant. There's usually only one that goes negative terminal to the actual chassis. All right, and you can imagine if you had a problem on that ground right here, what circuits on the vehicle do you think would be affected by that? Think it'd affect like the headlights, but not the taillights, or maybe it would affect the computer, but not the power windows. I'll give you a clue. They all use that thing. So if you have a whole bunch of systems affected, sometimes what we're trying to do is say, like, what do they have in common? Right, so you all came to school today. If everybody coming from Temecula was not here, they were all late, I'd say there's probably something going on the 79, because you're all coming from Temecula, right? Whereas if everybody who's coming from the north was late, well, I guess the 79 could be north too. Maybe like Lamb's Canyon or something, right? So if you have a whole bunch of systems that are malfunctioning, it's possible that each of the systems has a failure, but you know what's more likely? Each of those systems probably shares something. They share the same road. If that road's messed up, they're all going to be affected, right? So if it's this one, that's going to affect all of your circuits. But if the positive goes into the fuse box, and then the fuse box branches out, and let's just say you have a problem in that fuse box, it could affect a whole bunch of different systems. So rather than you going really obsessive about, well, the headlights don't work, the headlights don't work, the headlights don't work, if you back out and the headlights don't work, and the power mirrors don't work, and the taillights don't work, and let's say the power windows don't work, I don't think I would diagnose the any of those individually. I think I'd back out and try to study the power source diagram or the ground diagram and see, do they share a ground? Do they share the power source somehow? And you'd be like, oh, okay, there it is. So if you're understanding what I'm saying, the main way you'd fix an electrical problem like that is just thinking and understanding. You don't just jump on the car and like start testing and swapping and goofing around, right? If you know what I'm talking about, you're going to back out and be like, well, if there's multiple systems that are down, let me see what they share. And that doesn't look like work to the brand new, to the rookie technicians, right? You're like, man, that master tech right there just sitting on the computer clicking. Well, it doesn't look like work, but the master tech may very well be researching the power source diagram or researching the ground diagram, seeing what they have in common. And ASE is notorious for that. Like just yesterday, I take these tests all the time to stay really sharp, right? So this one wasn't electrical, actually. It was A4, which is suspension, and it had a problem with a vehicle that was sagging in the back, and it had adaptive air ride. And in adaptive air ride, it'll actually level itself. So if you throw a whole bunch of junk in the trunk and it squats, adaptive air ride will raise the back up, and it'll look like you don't have a bunch of junk in the trunk. For example, bodies, products of various sources, these types of things. It'd be nice to have a nice car because then nobody knows you're hauling whatever it is you're hauling. You know, it'd be like, oh, hi, officer, everything's normal. There's not 1,000 pounds of stuff back there. It's things, whatnot, right? So, but in this particular question, the back was sagging and it didn't self-level. And all they do is give you a diagram. Look at the diagram. It's saying it could be an open in the sensor, it could be an open in the switch, could be open whatever. But you know what I noticed? The rear two airbags shared a ground. So one option is it has a bad left rear airbag and right rear airbag. And that's possible, right? We can't say it doesn't. It could have two bad airbags, but don't you think it might have one component is more likely to fail than two at the same time, I'd say, right? And if they share a ground, what do you think the ASE, what do you think the right answer was? It's the common ground. They both share the same ground. So if you had one bad ground, that would cause two rear air suspension bags to not pump up, right? So that's an ASE concept. And it's an ASE concept because it's a real life concept too, right? So now when we want to talk about testing these and starting to apply some new terms, right? We talked a little bit about these terms, but we're going to start applying them more. We want to talk about like continuity, for example. Good continuity would mean a good way that I remember this is when I worked mostly automotive, and then when I decided I want to get into teaching, I'm going to tell you it's kind of hard because, you know, all these automotive shops are open during the day. So you'd be like, oh yeah, I'll be a technician, mechanic, whatever. Great, you got to be here during the day. That's when the customers are here. When do you think most of the teaching opportunities are? Also during the day. There's some stuff at night, but there's a whole bunch of people who could teach at night, right? So like for me, when I first wanted to do it, I was like, oh, I'll work during the day and then I'll teach the evening class. And then I realized that's what everybody was trying to do. Everybody was doing that. So it's like, all right, how can I mix this up a little better? And plus, how could I also make it so I could take classes during the day to get higher level degree to be more competitive? So I took a job on the railroad, and I didn't like pound steaks. It's not like the old song, I was working on the railroad. I was a diesel mechanic. So these diesel electric locomotives would roll in, you know, I would do diesel mechanic type work. It may be engine work. It may be air brake stuff. It may be leaking water pumps. It's the same as automotive, except it's diesel and bigger. But part of the reason I took the job was because I could get night shift. And I'm going to tell you, I promise you right now, I hate night shift. Like beyond, it was not, what do you guys think night shift hours are? Like what, like evening?
I'm on work 5 to 5 in the morning.
Yeah, so mine was 10 p.m. to 6 a.m. Yeah, I'm not made for that. But I did it so that way I could get paid full pay, you know. That was, 13 years ago, 12 years ago, somewhere in between like 9 and 12 years ago. And that was $34 an hour. So they're probably $38 an hour now. Straight hourly benefits, pretty good. You know, it's a good career opportunity, but honestly, I'm just gonna be real with you. I only did it so that I could get that stupid schedule so I could start teaching during the day. You know what the worst thing about nights was? That I was still teaching during the day. So I wasn't really sleeping that much, like a few hours a day. So it was great, but what I learned a lot from that job was there's 3 shifts, right? First shift was 6 to 2, second shift was 2 to 10, third shift was 10 to 6. So when I would roll in at 10, I needed to know, like, they'd literally put me on a locomotive that the person before me just worked 8 hours on. And like, I'd show up and I'd be like, what's done? What's not done? Like, they got the turbo mounted. Are these bolts torqued? Are these bolts just hand tight? So I'd spend a lot of time like rechecking to figure out what they did and what they didn't do, right? That's bad continuity. There's no continuity between second and third shift. So I started to try to fix that. And, you know, a lot of it was led by management. So they would say, you know what, we're so obsessed with having second shift work right till 10 so we get a good value, that third shift shows up and wastes an hour figuring out what the heck is going on. So they started saying, second shift, stop working at 9:30 and write down where you're at. What did you do? The turbo's in, the bolts are torqued. The turbo's in, the bolts are not torqued, right? So they made it so that they'd write a little explanation, and I'd get on the job and be like, oh, what second shift do? Those slackers. Second shift is the laziest shift. Actually, no, honestly, it's third. But, you know, I'm on third, so I can't be like, turn on my own people. I'll be like, second shift slackers. Of course, when day shifts comes in, they're like, third shift didn't do anything. They just slept all night. So I'd look at the turnover and I'd be like, okay. So that's how we got good continuity. See, continuity is like a good chain. It's a good connection. It's continuity. What else do I say? Electrically, you know what that means? Remember we had the path for electrons to flow? If you have good continuity, it's the path is easy for the electrons to flow. It's not disconnected, right? When I started at the railroad, second to third shift was very disconnected. I had no idea what happened on second. And then when I got better continuity, we were connected. We didn't overlap necessarily, but there was good continuity there. So that's really what continuity means. So let's just say if I said something had good continuity, that means it's not disconnected, right? It would mean it's easy for the electrons to flow. Well, that's going to come with a number. Did you know that? When you use the meter and you put it on ohms, it's going to give you a number. The higher the number, the more resistance, right? So the higher the number, that would mean I've got less connection with second shift. I don't really know what they're doing. Whereas if I've got a good continuity, that number is going to be lower. Make sense? So continuity is one that gets people a little confused. If my wire's good, I could do a continuity test. And I put my meter on one end of the wire, and I put it on the other end of the wire. And if the continuity is good, you know what my meter will do? It'll like beep. You can turn on where it'll beep or something. It'll beep, right? So why would we use that? Let's say you were trying to test some wires, but you weren't sure if the wires were good. You could put it on one end of the wire and touch the other end of the wires until it beeped to find out, like, where does that wire go? In auto, we don't usually need to do that because the wire color is the same. So if it was, you know, if you're working on a circuit with a red wire, you're probably like, oh, the red wire's here. Let me go to the other end. The red wire's there. I know it's that wire. But on locomotives, they didn't do wire colors. All the wires were the same color. And those things are like 50-something feet long. So it'd be like, oh, is the wire good for the light? They don't exactly have, they kind of have tail lights. You could call them tail lights. It'd be like, is the wire good? Well, I don't know. If you wanted to check continuity, you'd run the meter way up there, put on the wire. You run the meter all the way to the back, and you could put on continuity, but the problem was you wouldn't know which wire. So you'd be like poking around. You could have it beep. The beep is very convenient. That's used a lot for like electricians, because if you were to bust this wall open, the wire colors are all the same color. They're using like Romex inside the wall, and the power, because it's ASE, it's a little different, is black. And the neutral, it's not a ground, is white. And the actual ground is probably just bare copper. And then if you're going to do like a three-way switch, or you just want to pull one bundle of wire, they'll have a red one. And so you could use a white one for one thing. Like maybe if it's a ceiling fan, you might use like the white wire for the light and the red wire for the actual fan. And that way you can have two switches, and one will do the light, one will do the fan, right? But when you go to the fuse box, you got a whole bunch of black wires, a whole bunch of red wires, a whole bunch of white wires, and you have no idea where they go. Continuity test makes a lot of sense for like electricians. And that way you can find the end, beep, beep, beep. But for us, we don't do true continuity that often. Like if you wanted to measure whether a switch had continuity or not, we're probably not going to call it that. We're probably going to say, how much resistance does the switch have? And you'd put your meter on ohms, and you'd put one end on the switch, you put the other on the in of the switch, you put the other end on the out of the switch, and then you'd turn the switch on, you'd measure how many ohms, right? And then you'd compare it to what's good. So like a switch should have like maybe 0.2 ohms or less. If it has 0.2 ohms, that's a pass. If it has 0.1 ohms, that's a really good pass. If it has less, that's less. Less is good when you're looking for like a good continuity, good connection. If a switch should have 0.2 or less, and you put your meter on there and you measure 10 ohms, that switch is bad. That's a fail. Make sense? So continuity, it's one way to say it. For us, it's mostly going to be resistance. So if I say measure the resistance of that, it's actually the exact same setting on the meter as continuity. So if you want to do continuity, you put it on ohms. If you want to measure resistance, you put it on ohms. And I've talked with some people in the past who are like, you measure resistance when it's a resistor. Remember the resistor with those different colors? You measure resistance when it's a resistor. But if you're measuring a wire, you measure the continuity. And it's like, no, it's the same thing. It's literally the same thing. It's just a different way to say the same thing. If you have low resistance, you have good continuity. If you have bad continuity, you have high resistance. Kind of get it? You picking up what I'm putting down? All right, very good. And so the other thing is, things that transport electrons should have very low resistance. All right, I want to make sure you understand that. If it's a wire, it should have low resistance. If it's a switch that's turned on, it's connected, it should have low resistance. All right. If it's a light bulb, it shouldn't exactly have low resistance. It should have the specified resistance, right? So in the circuit, remember we talked about the load. The load does work. The load should have resistance, not just low resistance. So like if it's a light bulb, it might call for like 4 ohms. 4 ohms of resistance would be good because the load should have the resistance. And then is it going to warp your mind when we cover this a little bit? It's a little hard to understand, but when something has resistance, it consumes voltage. So if we started with 12 volts and you try to send it through a switch that has resistance, that switch is going to consume voltage, and now you don't have 12 anymore. Now you have 10 or 6 or 2. That means that the load itself, which should have the resistance, doesn't get the voltage that it was supposed to get. All right, kind of weird, huh? But don't worry, we're going to cover like 3 different ways. That was just to start to get you thinking, right? Things that just transport electrons, those should have low resistance, good continuity. All right, so like for example, right here we're testing a blower resistor, and so this is a good electrical test. If we wanted to know if this blower resistor was good, you could literally remove it from the vehicle, put your positive on the in, your negative on the out, and there will be a spec. Maybe the spec says something like 1.2 to 1.6 ohms would be good. If that was the spec, is this good? Can you read the number? 1.4, that's good, that's a pass. Don't sell the blower resistor. You just tested it and it passed. So it's good. So don't sell it. Make sense? That's what we do. What we don't do is, oh, customer, you have an issue with your blower motor? Well, I checked with ChatGPT and that said, go ahead and replace the blower resistor. That's the most common. Boom, I put it in there. Like, that's negligent. You can do that. You could start your whole business based on that. We do no diagnosis ChatGPT does the diagnosis. And well, ChatGPT is not going to issue the customer a refund. But if the customer doesn't want a refund, that's fine. But typically, when you go to sell a part, like this part, you might be able to get this actually pretty cheap. But on a newer one that's a blower transistor, that might be 100, 200, 250 bucks for a blower transistor. If it's a resistor, it might be 30, 40, 50, 60. If you can test it and bill your hourly rate and have the test be cheaper than swapping the part, it just makes more financial sense. Pay the technician to do the test rather than just throw parts at it or have ChatGPT pick which parts to shotgun in the car. Make sense? So a lot of what we're doing is we're performing a test to prove if it's good or bad. That's what we want. If we test this and the spec was 1.2 to 1.6 ohms, and let's just say we measured OL means millions of ohms, more than millions of ohms. If it should be 1.2 to 1.6, but we measured millions, is that good or bad? And you confirmed it, and now you have perfect justification for replacing the part. And then if you put the part in and it doesn't fix it, well, it technically could be a bad part, but I'd probably just redo the same test, just remeasure it, right? And be like, oh, yeah, now it was OL, but now it's 1.4. Yeah, this part's good, but it still doesn't work. What's that tell you? Yeah, and that's okay. Like, that's fine. It sucks because the customer thinks you're lying, but that's why it's very important. You did the test, you wrote down your numbers. The customer tries to sue you, and you come in and you're like, I tested the blower resistor because I was following the service manual, and it said 1.2 to 1.6 ohms. The original one said OL, so I replaced it. Anybody, any expert witness or any professional they call is gonna be like, okay, you did good. That's what you're supposed to do. But then it still didn't fix it, and then you'd say, yeah, and I went in and I remeasured, and after the new one was in, it measured 1.4, but it still didn't work. We'll all come to the same conclusion. There's something else wrong. That's not your fault. You know, I mean, the customer, they tend to discount us. They tend to be like, they're ripping us off. They didn't put the part in. Remember that from the strategy-based diagnosis. We just know the customers don't have a ton of respect for what we do typically, but that's okay. What's not okay is if you get called on the carpet, you get hauled into court or whatever, and then they say, why'd you replace the blower resistor? And you're like, well, I asked ChatGPT. ChatGPT said to do it. And they're gonna be like, that's kind of negligent, right? It's the same as a doctor. If you really think about it, the doctor has no business just throwing medication or whatever at, and being like, oh yeah, you came in and your arm hurt. I checked with ChatGPT and they said it could be broken to put a cast on it. And be like, did you do an x-ray or not? Right? If they did an x-ray, then they're not negligent. But if they didn't do an x-ray, then it's kind of like, you treated a broken arm without verifying it was broken? See? So that's how you got to think. Okay, very good. And then if we get into starting to do some of these specific other measurements, we're going to talk about these multiple times. So this is one of the things you have to know. And a lot of times they say you have to hear the same thing 3 times to understand it. So this is the first time, but not the last. Technically it's the second time, but all right. So let's just say we got a problem in the circuit. Let's pick, now you know what continuity is, right? Continuity would be good connection throughout. Let's say we got an open. What do you think an open is?
No voltage is going to go through.
Exactly. So a full-on open would be like if you had a wire, it was broken like all the way, right? So if you had a broken wire, what would that say about its continuity? Bad continuity, no continuity at all. Whereas, and you're right, if we start to look in the voltage, if it's a broken wire, you're going to have voltage on one end, the side that comes from the power, right? But then where it's broken, on the other end, you're going to have no voltage. You're going to drop all your voltage. So if the battery source voltage is 12.6, you're going to have 12.6 on this end, you're going to have 0 on the other end. That's a full-blown open, okay? An open's completely disconnected. And you could check that with continuity test, and you'd hook up one end and the other end, and your meter won't beep. Or you could look at it more how we do. You check resistance, and in a resistance, when you measure something and it's open, the meter reads OL. We'll cover this again, but OL means out of limits, Some textbooks call it overload. I don't like that term because you're not overloading the meter. It's not too much. It's like the meter is able to see ohms, thousands of ohms, which is kiloohms, millions of ohms, which is mega ohms, but after that it can't see. After that it's out of its limits. So if I see OL, I'm like, wow, it's got more than millions of ohms, it's out of limits. That's just open. So I'll never be like, oh, it has trillions of ohms, and be like, it's just open. Like, whatever, at that point it doesn't matter. Make sense? If you've got so much money, it's more than billions, you're just wealthy. At that point, it doesn't matter if you got 100 trillion or a 200 trillion, you just open. Make sense? OL, out of limits, out of what I can even comprehend. Make sense? All right. So if that's true, then when we talk about high resistance, how do you think that's different? Like an open is kind of like a high resistance, but a lot of times in auto, we look at them differently. An open's like totally open, whereas high resistance is like, well, there's a connection, but like not a good one. That would mean there's not good continuity, right? It doesn't necessarily say for sure it's open. That's why continuity is vague, and we don't totally like love that. But if there's high resistance, that would mean if we were to measure the resistance, it's going to be a high number, right? So if we should have like a 0.1 ohms or a 0.2 ohms, if it's high resistance, what type of number you think we're going to see? Give me a number, what'd you say?
Like a lower number?
Lower number would be less resistance. That'd be better. Higher resistance would be more resistance, right? So if I said 0.1 or 0.2 is good, give me an example of high resistance. You probably won't be wrong. Give me an example. 0.3 is a little high, but what about 300? That's like a lot high. So an open is when things are binary, you could say. It's either open or not open. But high resistance is like, well, it's not as good as it should be. It's not like 0.2 ohms, but like it's not a full OL. It's somewhere in between. Get what I'm saying? If a mouse chewed a wire and it was separated like this, that's an open. But if a mouse chewed a wire and like chewed some of the strands, but there's still a couple strands in the copper wire and some corrosion got in there, that's a high resistance. If you had a terminal and it got water in it and it corroded it and it's kind of rusty, that's probably a high resistance more so than an open, right? So to an extent, who cares? It still needs to be fixed. But as a matter of fact, it's nice to know which it is. So if you've got an open, I'm not looking for like a little corrosion on the terminal. Like I'm looking for a fully open circuit. Whereas if I measure high resistance and be like, all right, my brain's flipping around to like, let me look for corrosion and rust and loose connections and that type of stuff, right? So that's really the difference. So if there was no continuity with second shift, that means I know nothing about what happened. There's infinite resistance. I didn't even speak to second shift. I have no idea. Whereas if there's some resistance, that'd be like the second shift technician has sloppy handwriting and I can read some of the words, but there's too much resistance here. I don't exactly know what happened. It's kind of like that, right? So good continuity is low resistance. Very good. High resistance is sort of like, all right, it's not really working out that well. Too much resistance. Example, dim bulb. Remember the dim bulb? Dim bulb, probably going to be high resistance, right? Open, what's the bulb going to be?
Not working at all.
In-op completely, right? So if the bulb is out, I'm probably looking at an open. If the bulb is dim, I'm probably looking at a high resistance, right? Just right off the bat. And you know, sometimes when I hear people's explanations, I'll go put students out on the car and be like, hey, what'd you find? And they'll be like, oh yeah, it was an open. I'll be like, the bulb was dim. Opens don't cause dim. So I know you're full of baloney. And I can really call you out. All right, and then let's say we got a new one here. A short. A short. What do you guys think that? I mean, you can read the words, but like... Yeah, it could be. It could be dangerous, right? So, what were you going to say? Could be, yes. So, but I want to define it really clearly because I'll give you the justification for why I want to spend so much time on these. I had a service advisor. Do you know what they do in the dealership, kind of, or no? The service advisors don't fix the car. Customer rolls up, talks with the service advisor. And this guy, he was good. I mean, he's still, I'd say loosely like a friend. And I liked him, but his technical ability was low. Actually, he was a service advisor. Now he's like a service manager, director or something. So he's moved up, which makes sense. He was actually really good with dealing with customers. Customers would come in and he would, get them to feel like, we care, we're going to fix it, give us a good review, don't complain. He's good at that. But definitely couldn't fix a car for sure. Not at all. Not even slightly. All right. So when I would deal with an electrical problem, back in the day, things have changed, okay? But back in the day, the technicians would write on the back of the repair order what we did. So I would write, dim bulb, found high resistance at this connector. And, a lot of times what he would do is he would take what I wrote on the back and he'd have to type it up in something to give the customer. Now, things have changed. Now, we just do it ourselves generally. We're just going to type it up ourselves. There was a lot of these problems, and so, but back in the day, when I started by the time I was really a technician, I was in my 20s, right? So when I'm in my 20s, I could type. When I had to take a typing class in school, and I was doing the hunt and peck like this, right? And the teacher came over. He was a mean old guy, and he put a shoebox over top of the keyboard so I couldn't see my hands, with little cutouts where my wrist would be. I was like, this guy is such a jerk. And he's like, learn. And I'm like, fine. And actually, that was the nicest thing he ever did for me, because I could type like don't have to look, none of that. You all should be able to do that. If you can't, you might consider working on it, right? But when I started in my 20s, the people in their 50s, they didn't do typing. Like they might have done that might have been a thing, but they weren't really using computers like, I'm going to say loosely, us. So they would handwrite it, and then the service advisor would retype it. So I would handwrite it, and I'd give it to him, and he'd retype it, and he would change my high resistance into shorted wires. And I was like, dude, that's not what I found. And he's like, whatever, they're shorted. And I'm like, no, they're not. They're high resistance. There's high resistance. It's totally, it's wrong. It's like not factually accurate. So I'd get in these arguments and be like, and he'd be like, it doesn't really matter. The customer just wants the write-up. And to an extent, he was kind of right. But here's where he was kind of wrong. If anything ever went down and that rolled into court, they're reading what he wrote, and I'm going to have to try to defend myself. I never did, by the way. So I talk a lot about going to court, but technicians, we don't normally do that. But if you know it's a possibility, you're going to do things the right way. It's just better for our whole industry, right? So I was kind of like, no, just type exactly what I wrote. Don't change it, because you don't really understand. And my stories were very detailed, and he didn't want to type that much, so he'd be just shortening it, right? So what a short is, the circuit should go all the way over here and around and there. And you know what a shortcut is? A shortcut is a short, right? It's a short. It didn't go all the way around. It went from somewhere on the path and it cut over and it made the path shorter. That's all a short is, okay? Technically, that's it. Technically, if we were to look like back here, do you remember this ground? What would be crazy is if I took a screw or a bolt and I sent a screw through this cable and bolted it into the frame in another spot. That would technically be a short, because the electrons should go all the way through this wire to here. But if somehow the electrons bypassed this and went up here to the screw that I accidentally sent in there, that would be a short. But a short doesn't necessarily mean fire. So a short just means the path is shortened. If I were to short to ground something that was already grounded, who cares? It makes no difference. It doesn't really matter. It's just technically shorted. The reason I say that is you got to understand, if you see a ground wire that's pinched to ground, you're like, oh my gosh, a short. But it was already grounded and now it's shorted to grounded just in a shorter path. It made no difference. It should still be fixed, because it's not, exactly how it should be, and that could maybe corrode and cause a problem over time, but that did nothing. The ASE is pretty normal for like, they'll take a ground and they'll short it to ground and be like, what caused the fuse to blow? The ground was shorted to ground? No, that didn't. Go ahead.
I always thought if it's shorted out, it's going to be a higher voltage where it shouldn't be.
Kind of. And so now I'm going to tell you what most of the time a short means. Technically, all it means is the circuit is shorter. But generally, if it didn't affect it, we're not even talking about it. So here's what's very common. If a short were to be across a load, this is the common one, you take the positive side, right? And it's supposed to go through the load. Let's make the load the light bulb. The positive side should go through the light bulb and then become the negative side. And that light bulb, remember how the light bulb should have resistance? The resistance should slow down the flow. But if you were to short the positive directly to the negative, now you have no resistance. There's nothing to slow down the flow. So now you have unlimited electrons, just like, hey, we no longer have to work our way through the load. We can just go directly to the ground. And that's going to be a lot of amps and make a lot of heat and make things catch on fire. And that's exactly what it does. That's the reason that we put a fuse in there. Remember the fuse, how it sacrifices itself, right? So if by chance, let's just say it's the headlight circuit and you get in some sort of a minor fender bender accident, right? And the positive gets shorted right to the chassis ground. It's okay because it's just going to blow the fuse, right? Because it's going to bypass the load. It's going to bypass the planned out, designed resistor. It's going to have no resistance. And then when we look into Ohm's law, like we looked a little bit, right? You remember, well, if you were to look at that diagram we have, I'm going to do it. I'm going to back way up, okay? Because this is so important. All right, remember Ohm, how the Ohm slows down the amps? What if we were like, ohms, we're going to just totally loosen up. We're going to take that rope away from you. Now you could just see tons of amps are going to go through there because there's no tightness on the rope, right? So that's the visual. If you have a short, a lot of times it means it unintentionally eliminated the ohms in the circuit, which means you're going to have way too many amps pushing through, right? Now the voltage generally stays the same in a car. So what really controls the amperage is the amount of ohms. And ohms is resistance, correct? So if we were to have that short and we were to have no ohms, we'd have way too many amps, and that's when we blow our fuse. Or let's just say somebody was really bad and they wired up some really cool, fancy LED light bar, and they were like, you know what, I don't really need a fuse, no big deal. And they just went directly to the positive and negative of the battery, and they're running that with no fuse. And then let's say it gets shorted out. If there's no fuse and it gets shorted across the load, that means there's no ohms. That means there's lots of amps, right? Lots of amps. Well, what's going to happen? And bingo, exactly. The maximum number of amps will flow through that wire until it starts to get hotter and hotter and hotter, and it will catch the insulation on the wire on fire. And then it's on fire, and then that's, for all we know, I mean, you guys have seen cars on the side of the road on fire. It may be something as simple as that. It may be somebody who took an electrical class and missed this lesson, was like, yeah, I'll just put it right there. I don't need a fuse. The fuse is there to limit it. So if you have a wire that can handle 13 amps, you're going to have a fuse that can only handle 10. So if it ever gets closer to the 13, like by the time it hits 10 amps, boom, the fuse is gone. And that saves the wire. Not because wire is expensive, but because if the wire gets hot, it catches on fire. That's it. It's really that simple. The fuse can't really catch on fire because it's a little piece of metal inside plastic, and it heats up. And when we say the fuse is blown, what we really mean is so many amps went through that the metal in the fuse melted, and it's blown. Okay, but that's technically what it is. You want that to happen in the little plastic encased fuse. That's its job.
So it becomes an open?
Yeah, bingo. It was good continuity, then it has bad continuity. It had low resistance, and now it has high resistance. It had a good connection, and now it has an open. So the fuse is open. And that's mostly how I write my story anyway. If the fuse is open, I'll say the fuse is open. You could say the fuse is blown, and that's okay. I mean, like, we get it. But if you said the fuse was shorted, it'd be like, the fuse itself was shorted? And he'd be like, yeah, it's the same. I'd be like, no. That's not. If I'm saying that there's an open, that means there's an open in the circuit. A high resistance means there's too much resistance in the circuit. And a short means something's short-cutting, right? Don't switch them up. Those are all totally separate and different things. Okay, so that's the most common example of a short. And so, like, for example, if it was, let's just say the wire was pinched to ground and it blew the 10 amp fuse, what you don't do, okay, we're going to talk about how to diagnose it, but what you don't do, you could put another 10 amp in and pow, and it blows that one. Now it's an open. You're like, let me put another one in, pow. If somebody's diagnosed an electrical problem, they got a big old pile of blown fuses, it just means they don't really know what they're doing. It's fun, but it does cost money and it's wasting time. What you don't do is be like, oh, well, maybe it needs a better fuse. So we'll take the red one out, the red 10 amp, we're going to take that out. We're going to put in the upgraded yellow 15. That now the fuse can handle more amps than the wire. The wire is the thing getting hot and catching on fire. Okay, so that's the lesson. All right, and we'll cover that lesson a couple different times. But in a house, old houses, you know, they had fuses. So if you had, like, the lights went out, and they'd be like, oh, go check the fuses. You go, you open up this panel, cobwebs and stuff. And then you'd be like, there's these little glass fuses. Those fuses would blow. You could put a new fuse in. Newer homes don't really have fuses. What do they have? Breakers, yeah. Circuit breaker and a fuse, they do the same job. When a fuse gets hot, it melts, it blows. When a circuit breaker gets hot, it trips. So in other words, it separates and it's an open until you go and you turn it off and turn it on, and now it's reset. They could use circuit breakers on cars, but circuit breakers cost more money. There's really no reason that we should be having fuses blow. And if the fuse does blow, we don't really just want the customer to go and keep resetting it. Like, we want to deal with that. Now, in a home, you might trip the breaker because you powered on too many things. So, like, what's kind of weird in a home is you may have a 14 gauge wire that's good for 15 amps that goes to 2 bedrooms. And 15 amps is fine. But if you turn on every single light and plug into every outlet and turn the fan on in both bedrooms, it may very well be over 15 amps. It's not that there's a short, it's that you turned on too many things all at once. It could trip the breaker. That's why in a home they have a breaker. Because it'd be like, oh, hey, don't run the blow dryer. I'm running the blow dryer. I got my space heater on. It's cold. You know, it probably can't handle all that. Now, if it were me, I'm automotive, remember? If it were me, I'd be like, well, then let's run 2 totally separate. Let's do a 15 amp for this bedroom and a 15 amp for that bedroom. And then you can handle everything you want to handle and they'll never trip. So, like, when I built my, it's really my wife's parents' house, but when I built that one, I ran tons and tons of wires. And like, why'd you run so many wires? And I'm like, well, this one is for that thing, and this one is for that thing, and this one is for that thing. And they're like, you're using too much wire. Just run one over there. It'll power all of them. I'm like, I don't want the circuit breaker to trip. And they're like, well, what are the chances of everything being on at once? And I'm like, well, I've seen it. So if you've seen it, that's because it was wired with, like, household electrician in mind. For me, you ain't tripping no breakers in my house. I'm gonna tell you right now, you'd have to have, like, a lot of stuff on. And it's probably never gonna happen. But I spent 3 times the money of an electrician because I was just thinking in automotive terms. In automotive, there's no reason for that fuse to blow because it's dedicated. We've got one wire for that power outlet, you know, the cigarette lighter. We got one different wire for the radio. We don't cheap out and run one wire to do both, and if you use both, it may blow the fuse. If it's blowing the fuse, something's wrong. All right, so here's an example of a couple measurements. So let's say, first one, it's a little hard for you to see, but the meter is on ohms right here. And if you guys can see that number, 0.005. Does that sound like a lot of ohms or a little ohms? Yeah, which is good. That's like good continuity. That's like very low number. And we're measuring, our red lead is right here and our black lead is down here. So between the red and the black, can you tell what we're actually measuring that line? Is that a component? Because it's just a line on the paper, but what's it indicate like in real life? It's the wire going to the ground. Exactly. So remember, I told you a wire should have very low resistance. We shouldn't have a lot of resistance when we're just trying to travel down the road, right? This just transports electrons. It should be low resistance. We're in agreement. Now, what about on the second one? Same measurement going from after the load to the ground. So we're measuring the wire. What did we get? OL. So OL means, do you remember what I said? OL means like it's out of the limits of what the meter can see. So when we should have 0.02 ohms or 0.2 ohms, or in that case 0.005 ohms, now we have OL. What's up with that wire? Is it high resistance? It's open. OL is like, it's full on open. Now if we were to have, let's say, 10 ohms, that would be a high resistance. An OL is really an open. OL, honestly, if it were me, I would edit this fluke and not say OL. I would just say OPEN, open. And everybody would be like, oh, I get it now. But I didn't make it. And I have no say in that. So I'm just letting you know. This is an example of using our meter to measure resistance, right? Low resistance is good continuity. This isn't high resistance. This is OL. This is like a lot of resistance. This means an open. Cool. Neither of these have anything to do with a short. So don't change my words. All right. And then like, for example, let's say this is a coil. We do a lot of things with coils of wire, but let's just make this for now a solenoid. We wrap these wires around this iron core, and if we give 12 volts in ground to these wires, it'll actually make this move. Or sometimes we'll wrap windings around other windings, and that's a way that we increase the voltage or decrease the voltage, right? But either way, if you wanted to test these windings, you could actually measure from beginning to end. So if the wire comes in here and goes out right here, and you want to know what's up with that wire inside, we can measure from here to here, and that's going to give us a number. And we should always be able to get a specification of what it should be. Sometimes they're hard to find, I'll admit. But if we have a resistance spec of, in this case, it may be 1,000 ohms. If you're supposed to have 1,000 ohms right here, and you put your meter on here and you measure 0.2, you're like, what? It should be 1,000 ohms. That's a lot of resistance. How's it getting little resistance? There's a term for that. Do you remember?
Short.
Exactly. That's a short right there. And if you can see, this one is visualized. There's a short right here. It's bypassing the circuit. It's supposed to do 20 loops, and instead it's only doing 10 loops because it's shorted right here. It made the loop shorter. So there's less resistance because it's shorter. Makes sense? That's a short. And now this may actually blow or not blow a fuse. It's hard to say. It depends on the details. If this is an ignition coil for the spark plugs, it's probably not going to blow a fuse, actually. It's probably just not going to generate a good spark, which means the car may not start. Or if it's one coil per cylinder, that means that cylinder won't get a spark. Do you know what that results in? A misfire. That cylinder won't fire, exactly. So if, you know, that's kind of a different subject, by the way. That's engine performance. But if you're in engine performance and you're like, oh, I think it may have a bad coil, it may have you measure the primary ignition coil resistance. And if it's lower than spec, it's shorted. If it's higher than spec, it's high resistance. If it's OL, it's what? OL, we call it generally. Like open. Yeah, exactly. And so how you word it makes a difference. Here's another example. Here we've got the battery. Remember, this side over here is the positive. I know because this side's going to ground. That's the ground symbol. So the positive goes through this thing. Anybody have any idea what that is? We're going to cover symbols, so if you don't, it's fine. But if anybody knows what this squiggly line is, exactly, that's exactly what it is. It goes, so the electrons go through the fuse, they go into this brake switch, which is open currently, and then right here, unfortunately, somehow it got shorted to ground. It got pinched, the wire rubbed through, and now you have copper up against bare metal, You took it to the 12-volt radio shop and they were trying to put your amp in and they sent a screw through your harness into the ground. These types of things. Took it to Sparky's 12-volt audio shop and they sparked it up for you. All right, so either way, this is a short because look, it should go like this, but instead it goes boop down. Now, if we were to examine this circuit, what's the thing on this circuit that does work for us? Think of examples. We talked about things that do work. They make heat, they make light, they make movement, they make magnetism. Like, what's the thing that's doing work on that circuit?
The bulb.
Exactly. The bulb is the load, okay? So all on this side, we should have low resistance, and then it should go to the bulb, and the bulb should have basically all the resistance in the circuit. And the way that's going to, and then after that, it should just be like low resistance to ground. What that's going to translate to is if there's low resistance on the ground, low resistance on the power supply side, that means all the resistance in the bulb should be able to consume all the voltage that's available, and that'll make it glow bright. But if we were to have, different than this image, if we were to have like an excessive amount of resistance in the switch, now the switch is going to consume some voltage, which is going to take away from the bulb. That would be a dim bulb. But in this case, it's shorted, and it's shorted before the load. So if we were electrons, we'd be like this. Okay, woo, go through the fuse. Let's close the switch in this example. And they go directly to ground. Was there anything to slow them down? Is there any load, any resistor? No. So we get way too many amps. That's when the amp guy doesn't have the rope anymore. Way too many amps. What's going to happen to the fuse? Poof, blown, right? That's an example of a short. And that's a bad short because it's actually shorted the positive right to ground with no load in between. That's a fuse blower there. What if we were to have a short right here to ground? Think about that. What if the short to ground was there? That'd be kind of weird. Then we'd have the electrons go through the fuse, go through the switch, go through the load, and they just take a shortcut to ground, but they were already going to ground. That'd make no difference in the circuit at all. It's technically a short, but it's a short to ground on the ground side that was already grounded. So like the customer has no concern. Still works. All right, but here's a tricky one. Down here, short to power, which for the record is much less likely. Can you imagine why a short to power is less likely? Think of what ground looks like in the car. If we had shiny metal, that's ground. There's ground all over the place. So if a wire gets shorted to shiny metal, it's shorted to ground. For a wire to get shorted to power, it's got to happen to get shorted to another wire that happens to be powered. Make sense? It can happen, but it's not as common. So in this last one, we got the battery. This is all positive stuff, right? The switches, by the way, the switches don't do work. The switch controls the circuit. So if I turn the light switch on and off, the switch itself isn't doing the work. Now, yes, I'm doing the work with my arm, but the switch is control, okay? So don't be confused. These are not the load. So there's a switch, another switch. Now down here, there's a brake light bulb. That's the load. That does work. It gives us light. But that's not the only one. Right here, there's a blower motor resistor. That is also the load, right? So what does a resistor do for us? Well, it generates heat. So the load in that case is kind of the resistor, but we're not really trying to use the resistor to generate heat. We're putting it in there so that it shares the voltage of the blower motor. The blower motor is the main load. And actually, this one's a little complicated because this one's a load as well. But if you notice, it splits off. This is what's called a parallel. So this has access to full power for just the blower resistor and the motor. And this has access to full power, and it's just for the bulb. So like these, you break this down into two circuits. The lower circuit's simple. It's actually the same as up here, basically. Positive voltage goes into the light bulb. The light bulb is grounded by the chassis. What controls this light bulb though? Can you tell? What turns the light bulb on and off?
That brake switch.
The brake light switch. So the brake light switch takes the power and it decides, give the power to the brake lights or don't give it. Make sense? Give it or don't give it. That's what the switch does. If you turn the switch off, that means don't give it, right? Turn the switch off, no voltage. But this is the problem. What if we had a short to power after the switch? Now you turn the switch off and say don't give it power, but it's shorted to power. So what's the status of the bulb?
Still be out.
Right there.
It's on all the time. But this is what's weird. Is that going to blow the fuse? No. So that's why I want to define the short clearly. A short doesn't necessarily mean the fuse blows. A short means it's a shortcut. So see, what should happen is electrons should come all the way through here and through all this, right? But instead they're like, nah, forget the switch and the fuse. We're just going to go right here. Boom. That won't make it too much amps though, because we still have the same amount of resistance in the bulb. So the bulb's going to slow the electrons down and it'll just work. But the problem is you'll turn the brake light switch off. You'll stop pressing the brake lights, the brake pedal, but the brake lights are still on. So it's a short because they've shorted the circuit. And now basically, if it's a short to 12 volts on the 12 volt side, well, it depends on exactly where. If it's right here, your bulb's on all the time. You got a problem. What if it was shorted to 12 volts over here? True, but if 12 volts is shorted to the 12 volt side, it won't hurt the fuse because it's already getting 12 volts. Now, if it was shorted to ground over here, yes, the fuse will protect it. But if this side is all power and you give power to what's already powered, it doesn't care. It'd make no difference at all. But where it got tricky is if we short 12 volts after the control thing, we no longer have control. You can't turn this light off. So, all right, and we're going to get up at this point. Actually, no. This circuit, this is what's kind of weird because this is parallel, and this is kind of a lot for this stage, but it's okay. I'll entertain. Because this is a parallel, this circuit kind of stands alone. This one up here kind of stands alone. They both have access to the same wire right here, but really after that, they're pretty independent. So if we had a problem down here, it wouldn't necessarily affect any of this. Now, if you guys are understanding, the 12 volt was shorted after the switch, the light bulb's going to be on all the time, right? Why is that a concern for the customer? Yeah, kill the battery. They'll be like, hey, my brake lights are on all the time. Technically, if you wanted to go even further, you'd have no cruise control at that point because your cruise control is disabled when you press the brake pedal. If the wire shorted to power after the switch, it thinks your brake's applied all the time. Your cruise control's disabled. You're going to get quite a number of little issues, right? But that's just an example of short to power. Now, if we look at the top, right, because that's where we're going, the ignition switch right here, if you turn the ignition switch off, we should have no voltage here. So this one's kind of weird. It would be more like the actual symptom of this would be when you turn the ignition switch of the car off, the blower motor keeps running. All right, but I'm gonna explain to you why, okay? And again, trust me, we're gonna cover all this stuff a couple times, but this is the first time you've heard this. We should have 12 volts coming up to the switch, right? When you turn the ignition switch off, that's where the key is. You turn it off, right? That should open this switch. And remember, the switch gives power, it doesn't give power. So if we turn the switch off, it doesn't give power. That means none of this is going to work over here because it's not getting power. The problem is we've got a short to power after the switch, which means when you turn off the ignition switch, it gets power anyway. So then the power is going to go through the blower motor switch, which let's assume you leave on like the speed number 1. Speed number 1 is going to go through this resistor and this motor, which means they're going to split the voltage and the motor is going to turn slowly, right? This resistor gets 6 volts and this blower motor gets 6 volts and it turns slowly. You turn the ignition switch off, it should turn off, but it doesn't because it's shorted to power after the ignition switch, which is supposed to take power away, but it can't because it's got another source of power afterwards. Kind of makes sense? Those are examples of shorts. All right, now what about, and we talked about like even different types of short circuits, but let's say we focused on a little bit more like resistance now. I think we're probably rocking on shorted. If here you had some resistance, you should have your voltage coming off, going through the fuse, going through the switch. Let's assume we close the switch. That means you turn it on. It should go to the bulb, and then it should go to ground. The bulb is the load, and let's say that the bulb is 4 ohms, just for math. If it has 4 ohms, it should be the only thing with ohms in the circuit. It should be the only thing with resistance, which means it should consume all the voltage. That would mean it should be pretty bright. But if you have unwanted resistance somewhere else, that's added resistance, right? So let's say you had 4 ohms right here, and you had 4 ohms right here. Now they have to share the voltage. It's going to be dim. So that's an example of high resistance. The high resistance could be here, or here, or here, or here. This is supposed to have resistance because it's the load. It could be here, or here, or here. Anywhere in that whole circuit, if there's high resistance, it's going to mean that the bulb has to share the voltage. It's going to be dim. If you wanted to do Ohm's law on that, which we will, but I'll just breeze you through it a little bit. If you look at, let's go with that same picture. Back it way up, which is fine. I'm allowed to do that. We're supposed to have this picture right here. You see the ohm? What if we took an ohm and we threw another ohm guy over here and they were both pulling up on the rope? Don't you think that's going to really lower the amps? That's why it's dim as well. There's 2 ways to look at why it's dim. Way number 1 is when you have multiple resistors, each resistor is going to consume an amount of voltage, right? So when the bulb should have got 12 volts, instead of getting all 12, it got 6 because the other resistor took 6. The resistor can be before or after, it'll still take 6, assuming it's 4 ohms. Now, if you had a 4 ohm bulb, right, and this is where Ohm's law will come in later. If you had a 4 ohm bulb and you had a resistor of like 4,000 ohms, that 4,000 ohm unintended resistor is going to take like a lot of voltage. Your bulb will barely be lit at all, if maybe not even at all, right? So the amount of voltage they consume is going to depend on how much resistance. But for now, we'll make it equal. So if you had this guy pulling up with 4 ohms of force and you added another homie pulling up with another 4 ohms of force, you're going to have very low amps, and that's the second way. The number of amps going through are literally the quantity of electrons flowing through the circuit. If you have less electrons, don't you think it's not going to be as bright? And so that's really the effect of high resistance. And that's right where we were at, which was there. Make sense? Unfortunately, this resistance right here is going to make that bulb dim. Maybe it's corrosion, maybe it's loose connection, maybe, these types of things like we were saying. Okay, cool. And now hopefully you'll know how to measure that because we talked about ohms. You could actually measure the resistance. You could be like, oh, the bulb is 4 ohms. Good. Measure the ground. Oh, the ground is 4 ohms. The ground shouldn't be 4 ohms. The ground should be like 0.2 or 0.1 or 0.005 or something. Make sense? Very low. All right. And then this one is your first exposure. You're probably not going to totally get this, but it's okay. When we start talking about finding the high resistance, I mentioned it last time too, but when you talk about finding this high resistance, you could measure resistance. But to measure the resistance, you got to actually disconnect power and measure it individually. If it's high resistance, remember how I told you it's going to consume voltage? I would rather measure it like that. So for I'm going to say 90% of the class, we're going to speak in terms of measuring the voltage and determining how much it dropped, okay? If the voltage drops a lot, that meant where it dropped the voltage had high resistance, all right? But it's kind of like the cause and the effect. The cause of high resistance is a drop in voltage. So a drop in voltage is the effect. So rather than us measuring the cause, a lot of times we just measure the effect, which tells us exactly what the cause is. Make sense? So if I were to go back to this one and I were to say, remember this is 4 ohms and this is 4 ohms, you could measure that, or I'm going to tell you we could measure it with voltage. If I had 12 volts here, I had 12 volts going into the bulb, I ended up with 6 volts coming out, and then I ended up with 6 volts dropping across this resistor. This dropped 6 and this dropped 6. Aren't those the same number? That tells me the resistance is the same, even though I never measured the resistance. Right? So most of the time, that's what we're doing. The reason that you need to know is because there are times where you're going to want to measure resistance, and there's times where it's better to measure voltage. And measuring voltage tells you resistance, and measuring resistance tells you what the voltage will drop once you apply it, right? So it's sort of like being kind of like bilingual. It's like if you bat right-handed, but you can also bat left-handed. So it depends on this. Maybe you got a different pitcher. Maybe you're like, oh, if I bat left-handed, I could hit a home run, but you got to be both. Make sense? If it's snowboarding, you got to go both ways, left forward or right forward, goofy or regular, both.
I have a question. You know how you were talking about the voltage drop?
Yes.
And it would be the same if there's no change in resistance?
Mm-hmm.
Where would you put your probe? Would you put it, one I know you probably put before the bulb and after the bulb. But that one?
There's 2 different ways to do it. So I'm gonna answer, but for everybody that doesn't get it, don't stress. We're gonna cover exactly where to place the meter another 2 times, but I'll give it to you today. Let's say I wanted to know available voltage, and this is the main way I like to do it. I would check the voltage here. Let's say it's 12. So I'd put my black lead on the ground. I put my red lead right there. If my red lead's right here and I get 12, I'd then move my red lead along the circuit. And let's say I get to before the bulb and it's still 12. And then let's say I poke after the bulb and it's 6. If it was 12 and now it's 6, how much did it drop?
6.
Exactly. And then if I go down here and I say, oh, it's 6 right here, and then after I drop and it's 0, how much did I drop?
Another 6.
Exactly. So the way that you could do it that way, and that's how I normally do it just because that's how I like to. You can determine voltage drop by measuring the available at different points and then doing quick math, simple math. Exactly, just follow the path. And that's where I usually start. But sometimes the manufacturers would rather you come over here and you put your red lead right here and you put your black lead right here, at which point between your red lead and your black lead, they're both measuring like the amount of voltage. So if you have your red lead here and your black lead here, it's actually just going to measure 6 because it's saying at the red lead to the black lead, the difference is 6 volts. That's how you measure voltage drop. And that one's that one I usually cover second. It's not hard, but you got to kind of work your way into that. So if I wanted to measure voltage drop directly, I would put the load in between. I put the red and I put the black leads right next to each other. And if it says 6, I know it dropped 6. And then if I put the red lead here and the black lead here, it would show me another 6. You get the same numbers, but it's a different way to do it. And trust me, we're going to cover that again. So I knew that probably for 80% of people that's not going to stick, which is fine. All right, so again, what we're saying is the voltage drop of a circuit indicates that there's resistance present and current flowing or trying to flow. So if you measure voltage and you had 12.6 and then you move down the line a little bit and you still get 12.6, there's no resistance there. But if you started with 12.6 and you move down the line a little bit and now you're down to 12.5, that tells you there's just a little bit of resistance because you're burning up a little bit of your voltage. It's kind of like money, right? If you got $12.6 and then you used a road and at the end of the road you had only $12.5, it cost you about $0.1, 10 cents to use the road. That's a small fee. But if you get to the bulb and you had 12.5 and then by the end you had 0, that means you just expended all that voltage, which that's good because it's the bulb. You're supposed to spend all your money right there doing work. What you don't want is to be dropping voltage where you shouldn't. So like back here, we should not be dropping voltage on a ground wire. Remember, there should be good continuity on the ground wire. But if there's excessive resistance on the ground wire, that means we're losing voltage, and we're like, why are we losing voltage here? I don't want to lose voltage here. Well, you should know it's because there's excessive resistance. Yep, makes sense. And you'd write that up, high resistance on the ground, and that would be your diagnosis. All right, so mainly that's kind of the point of the voltage drop. So we can place a voltmeter across 2 points, and I'm going to show you how to do it, available voltage and voltage drop. There's 2 different ways to go about it. There's a time and a place for both. Available voltage, I like the best because it's the most logical and easy to explain, but sometimes your circuit's very long. So if you want to do available voltage, you have to stretch your meter way out, and you might not be able to reach. So sometimes you bring them closer together and you just be like, you know what? I'm going to check the voltage drop across the bulb, and you can do it right here, like right in front of you. You don't have to be all stretched out. So you definitely want to be able to do both. So like, for example, if I were to look at this cable, the positive battery terminal goes over to the alternator. If this is a wire, how much resistance should be in that wire itself? Exactly, which means how much voltage should it drop if there's not much resistance? Like, bingo. Bingo. A couple people are getting it. So what I would do, rather than disconnecting the battery and measuring resistance, which isn't a great test, by the way, I would rather test it dynamically, test it while it's working. I'm going to test the resistance really by testing the voltage drop. Okay, kind of makes sense now? So if I go ahead and I put my black lead here and my red lead here, and I start the vehicle, I should see how much it should drop. In this case, it dropped negative 1.27 volts, which means really these meter leads should be switched. And I first noticed that, and I forgot why I did it. The red lead at the alternator makes sense, but if your alternator is not really the source of power and your battery is, you should switch them. You always want your red lead at the most positive and your black lead at the most negative. And if you have them switched, no big deal. The numbers are the same. The reason it's negative is because it should be the other way in this case. Now, if your alternator is working really well, the alternator should actually have more positive. And then if the alternator has more positive, then you'd have a positive number because that would be correct. But 1.27 volts on a wire, that's too much. That would mean if your alternator's charging good at like 13, and if you're dropping 1.27, you're only really going to get like 12, not even. You wouldn't even get, let's say your alternator is charging at 13 volts and you drop 1.27 volts, that's 13 minus 1.27. You're going to see like 11.73 volts at the battery. That's a charging system failure. But is it the alternator? In this case, no. Your alternator's charging at 13, but it's dropping a bunch of voltage on the wire. So what's the actual problem? You can give it to me. In the wire. So if you change the alternator, it didn't fix the car. Make sense? If you just are like, hey, it's not charging, throw an alternator in it, boom, you didn't really do diagnosis, right? We should do these measurements when we're confirming what the problem is. And if you did this measurement, you're like, hey, I'm dropping 1.3 volts across the wire. It don't need an alternator. It needs a wire or wire repair or the terminal's loose or something's causing it to drop too much, and the something is excessive resistance. We just don't know exactly where, right? So just to give you an applied example of why knowing this is going to make the difference between fixing the car or diagnosing the car correctly or incorrectly, right? And then like when we talk a little bit about electrical sources, it come in many forms. It could be transferred between objects. We're back a little bit to the physics, and we talked about that a little bit. So like, for example, light, heat, magnetism, these are the types of things. And that's part of the reason we use electricity so much, is like we can do so many different things with it. You want to make something go, electricity can do that. You want to make something glow, electricity can do that. You want to make something, I don't know, warm, we can make electricity can do that. That's the only reason that we use it so much. It's very versatile. And then when we talk about sources, this is kind of zooming out and just giving you an overall. It could be fun. You guys know static electricity? That's fun. I'm sure when you were little kids, you'd know. Rub my feet across the carpet and zap my little brother. Pow! Or your cat or whatever. It's fun. That's actually one of the major sources. Like, for example, if you see a thunderstorm, that's actually really all got to do with static electricity. So in the thunder cloud, we got a lot of positive charges on the top. We got a lot of negative charges on the bottom. And the ground is going to be either positive or neutral. The more of a difference in electron buildup, the more potential, right? And that's part of the reason that this is helpful to tie it together is like, what is voltage? And voltage is a number that indicates a difference in electrons, like in density and potential. So if you have like a little bit of extra electrons up here, there's a little bit of potential. That's not enough to make electricity arc a gap of, think of how high those clouds are. They're 10,000, 20,000, 30,000 feet. You're telling me electricity is going to arc a gap of 30,000 feet? That's nuts to me. How could it possibly arc a gap of 30,000 feet? You actually already know this answer if you remember last week. Right? Because there's going to be a lot of resistance in here, right? That amount of air is not a good conductor. There's a massive amount of resistance. So how could the electricity overcome that much resistance? Well, if we were to tie that back to that picture, well, you can picture the picture. The resistance, the ohms guy, he's pulling super hard. So how are we going to actually get amps to flow through? Exactly. So when you got this thunderstorm, you have to have an extreme pressure difference, right? You have to have an extreme negative potential right here to actually become enough to lightning that all the way down the bottom. Now do you guys understand why at the skyscrapers they have the lightning rod sticking way up? If we have a lightning rod sticking way up, that's going to be closer to the cloud. Electricity is very predictable. Remember, it's not like random. Now the lightning bolts can look kind of random, but technically those electrons are just finding the path of least resistance to ground where they can equalize. It's got enough pressure where it's motivated enough to literally bounce those electrons molecule off of atom off of atom. But if you had a big ground rod right here that's a good conductor, it's going to go to the ground rod and go down through the building, and that's kind of, better than it hitting random things and people and stuff. And so that's also why you don't go with the umbrella, right? If your umbrella is sticking up higher, that may be the path of least resistance, right? So if you essentially just think when there's a thunderstorm, you don't want to be the path of least resistance. You ever hear people say, oh, I'm wearing rubber shoes, so I'm good. But like, trust me, if there's enough voltage to jump 30,000 foot gap, those rubber shoes are getting cooked. But they probably did help a little tiny bit. Now that's also why they say, get out of the water, because the water is a better conductor than the air, right? So now it should kind of start to make sense why we say some of these things. Now, how did this become so negative? It all has to do with the voltage potential and exactly the minute details of how static electricity works. To be honest, I don't really know. But if you drag your feet across the floor, you can actually build up a voltage differential. And then if you're charged very negative and someone else is not, you can share that negative charge. Pow! Pow! That's how you can shock people, right? So it's fun. And it's healthy. It's also fun if you can do it in the dark because you actually see your little tiny spark, the little chispa. We'll call you chispa from now on. Okay, kind of fun. And then the other thing is, in thunderstorms, it's pretty normal that it's raining. When it's raining, that's helping to add a path of lower resistance down because the water's a better conductor. And it will jump from droplet to droplet. Kind of interesting. And that's also actually how it's made too. The water droplets and ice clouds make like static electricity. Part of the reason that the lightning happens with the storm typically. And then what other things we could do? Well, let's say if we wanted to make electricity, we could move a conductor through a magnetic field. So generator, if you want to make electricity. If you go camping and you're like, hey, we want power so we can turn our lights on and do whatever, charge your phone or whatever it is you do, you could start a generator, right? Generator, you're going to put some sort of fuel in, let's say it's gas, and then you're going to start over. That engine will consume that gas in exchange for rotation. That rotation doesn't do any good to make electricity at first, right? So like if you just had rotation, you could make the thing go zoom around. It could, right? An engine can carry you around, but what we could also do is take that engine's motion and do just what it said. What's it say? Moving a conductor through a magnetic field. So if you have a conductor on the moving engine part and you have a magnetic field that's stationary, you can generate electricity. That's what a generator does. It moves a conductor through a magnetic field, and the byproduct is a production of electricity. That's what a generator does. So you start the generator up, and next thing you know, brrr, and the lights will come on. That's the whole reason why. But it takes work, because remember, it's a conductor, so that's something metal. And it's got to go through a magnetic field, and do you think there's going to be resistance? So you have to have something pushing it through the resistance, pushing and pulling and pushing and pulling, and that's what we do. For the record, that's also what an alternator does. When you start the car, the belt turns the pulley, when you start the car, the engine turns the pulley, which turns the belt, and that belt turns the alternator pulley, and the alternator spins a conductor through a magnetic field, and the result is electricity is produced. That's what charges your battery back up. And when you're running, truthfully, your lights and everything are all being powered off the alternator, really. The battery's there to buffer it, but your battery's only really discharging before the car starts or when you're at the drive-in and you got the lights on. That's why you need to start it, to recharge it. Cool. Another really cool one, we can convert sunlight into electricity through photovoltaic. What uses that?
Solar?
Yeah, that's correct. Solar's a great way to make electricity, except when it's dark. See, so like if you wanted to make your own power and you want to use solar, cool, but what do you do at night?
Backup battery.
True. And so you could double your solar production and have half of it run your house in the day and the other half goes into the battery, and then at night the battery powers your house. That's absolutely true. But a battery doesn't generate. A battery just stores. The actual PV, the photovoltaic, they'll call it solar, right? But if you talk with like a contractor, they'll be like, oh, a PV system. You know, like a PV system. Yeah, photovoltaic. PV system. So that can actually generate electricity from the sun. The problem is it needs to be inverted and it needs to be regulated. And that's why we have like inverters and, you know, it's not just, you can't just take a solar panel and shove it in the outlet. It doesn't work like that. You got to have the solar panel go through an electrical component that's going to make it 115 volts at 60 hertz frequency oscillating on AC. Like, so we need more equipment, but the actual solar panel, that's all it does. It's a pretty good one. Or we could even do chemical reactions that take place inside of batteries. So when I said the battery stores, that's true, but it doesn't exactly just like store up a bunch of electrons. Those electrons go in and those electrons get used for work to convert, I'm going to make it very simple, to convert your battery water into battery acid, right? Then when you're like, hey, I need more power, the battery will convert battery acid back into water and the product will be putting out electrons, right? So that's why the battery is a storage device, but it's a chemical storage device, really. It doesn't actually just store the electrons. Now, if it was a capacitor, technically the capacitor stores the electrons, but a battery stores energy in chemical form and it can absorb electrons and discharge electrons while it changes chemical state. It's kind of weird, but it's cool. So that's how we could generate electricity. We could also just simply rub two insulators together. That would be even kind of similar to your feet on the carpet. And then a lot of things are insulators. And like, let's say that you're pushing the shopping cart and the shopping cart has rubber wheels and the rubber wheels are rolling across the concrete in Costco. And then you go to open the freezer section and pow, you get a little shock. Yeah, that was you. That's because you were just rolling those rubber wheels across the concrete and you generated up a charge. And when you go to touch the freezer, that freezer is grounded. So that's a way of your excessive electrons to get out, or, depends on exactly how you look at it, right? Either way, there's an imbalance. There's more electrons or less electrons in one than the other. Okay, cool. Just part of the reason that a house has a ground. So honestly, those outlets, if you look at an outlet, there's the two that are like this, and then there's the round one that looks like the mouth if it's a face. That middle round one, you don't need that for the device to work. So that's what's weird about homes, is the ground is not really like supposed to do anything unless you have a malfunction, and then the electrons would be easiest to go to that ground, which literally goes to a steel rod that's driven into the ground, like a lightning rod. Every building has a steel rod that's driven into the ground, probably inside the concrete. So if there's ever an excess of electrons, it should want to go to the steel rod rather than to you when you go to unplug the shorted out toaster oven or something. It's very interesting. Ground is just for safety in homes. It's not needed to do work. That's what the neutral's for. And you could go, it's a little different. So I'll just give you little bits of how the homes work. Cool. So that's what we do. That's essentially the job. Good. And so this is more just talking about how you would zap somebody. It can be really fun. That's your little spark that you make. You build up a charge, and then you release it where there's not an excess charge. Just like this. Zap. Right there. Boom. Now, why is that a concern if you're at the gas station? If you do a little zap, and there's a lot of fuel vapor around, it can, yeah. So there are, statistically, there are a number of fires at gas stations every year. So now that we've talked about this, I'm going to help to clarify why some of the rules are the way they are. Like for me, when I go to pump gas into gas jugs, the sign says don't pump gas into gas jugs while they're still in the truck. So I'm generally following the rules. I take them out and I put them where? On the ground. Exactly. So you can't have a gas jug that happens to have a charge built up in it, and you go to pump gas into it, and now your feet are on the ground, the gas jug is charged, it makes a little spark to you, and now that's right next to the fumes, right? If you put them on the ground, that's where it's going to be safer, right? So when we say like discharging, generally we talk about discharging to the earth, to the ground. So if you slide off of your seat, you slide off your seat, don't you think you might build up a little static? One of the things actually that's a best practice is to go over and touch the grounding of the pump, touch the metal on the pump. Just touch it before you even start pumping. Because if you had any buildup, you touching that should actually equalize it. Now you have no static buildup. Then you grab the pump and you start pumping, right? A big thing that people get weird about is the phone. Honestly, from all my research, the phone is generally not. Have you ever been shocked by your phone? I mean, this isn't really a source of this. I'm not really sure why people take this seriously, because there's much less risk in this causing a fire from just a little arc, a little static discharge, than you sliding off the seat and going straight for the pump and not touching the ground. But honestly, I feel like I have a lot of information that people benefit from, but they don't want it, so I don't really try. So I'm just letting you know, because you're here. The safest thing you could do for real, get out, touch the little pump, touch the little ground, and then start pumping. Then you also get a lot of people who are saying like, turn the car off when you're pumping gas because otherwise it'll explode. And I'm kind of like, how? I see a logical path to sliding off the seat and grabbing the pump causing a spark. The car running, it's not generating static electricity. Everything's all grounded through the chassis and going back to the battery. I think that the car running is more an issue of ventilation and, maybe somebody forgetting to put it in park. That'd be a problem, right? The car running, actually, I don't see any substantial threat to. So you get places, the gas stations, they have these policies. And generally, I just follow, but once in a while, I'll ask or I'll poke a little fun at them. Like one point I was pumping diesel into a container in the truck, and the guy's like, "Oh, you got to take that gas jug out." And I'm like, "It's diesel." And he's like, "You still have to." And I was like, that diesel's like it exponentially harder to actually create a fire from an arc from, right? Like a diesel engine, you can't spark a spark plug and start a fire. It doesn't work that way. They're kind of like, it's dangerous. And I was sort of like, I'm gonna do whatever you say, but let's just talk a little bit. Like, how do you think diesel and gas are the same when they're being pumped? And we just have like fun little conversations. A lot of times the people at the gas, they have no idea. The gas station people they have a policy. Someone who made the policy probably knew, and they could have said, if it's diesel, it can stay in the truck, but if it's gas, put it on the ground. But then you're going to have to train everybody. No, they're just going to say put them all on the ground. But technically, I would have no hesitation with pumping diesel without taking it out and put it on the ground, because the way you ignite diesel is just way different, right? So even some of this stuff is impractical, but kind of fun knowledge. So by all means, to be the most safe, go ahead and touch something metal before you start pumping gas. But I'd probably not recommend engaging with the employees of the gas station. They probably aren't going to know. All right, so pretty fun. That's kind of what that's saying. Then if you're working on ECMs, like let's say we don't generally go into the ECU, but let's say you wanted to work on the actual circuit board. That's why in that earlier picture it had the little ground strap. Before you work on anything sensitive electronically, you should touch some ground, touch some metal, discharge yourself. Because one little static electricity zap of a computer chip and that chip is done, just the way it is. Cool. And there's also something called thermoelectric energy, and that's a lot of times how we can make heat, or how heat can make a voltage potential. So if we have differences in heat, we can actually generate voltage. And sometimes two dissimilar metals are joined and heated, and they call that the hot junction. And overall, that device is called a thermocouple. The reason that this is good is you guys know what a thermometer is, right? Thermometer has a pretty limited range, whereas if you're trying to measure magma, if you're trying to measure molten rock, that's going to be way too hot for a thermometer, but a thermocouple would do it. So if you have two dissimilar metals and they're joined and you heat them up, they will actually generate a certain amount of voltage. That voltage can be displayed on your meter. So if you bought a meter and you wanted to be able to measure temperature, you buy a thermocouple. You'll plug the thermocouple in. The heat, depending on how hot it is, will make a certain amount of voltage. Your meter with the thermocouple module will transfer that voltage into a number, and you can measure temperature with your meter. It's pretty neat. Way higher and way lower than a simple thermometer. You can get a very large range. So if you see a thing like, oh, this meter comes with a thermocouple, be like, oh, cool. That's what that is. That's how that works. Right? So like as an example, if you did 392 degrees Fahrenheit, you could get about between 9 and 15 millivolts, right, if it's loaded. So they're measuring millivolts to determine degrees. Cool. Kind of fun. That's what that looks like. On the vehicle, we've got one like this. This is a sensor. They generally may not call it a thermocouple. They'll probably call it an EGT, exhaust gas temperature sensor. So if it's a diesel or something, be like, oh, I got an EGT sensor. And you're like, oh, what? It's an exhaust gas temperature sensor. How's it work? Just like that. The hotter your exhaust is, the more voltage it'll generate, and that voltage will go to your ECM, and your ECM will be like, okay, now I know the exhaust gas temperature. We don't really do that on gas, but on diesels, we need that, especially when we're trying to do after treatment to clean the emissions up. We need to know the exhaust gas temperature because we're storing it in, a diesel particulate filter. And then when we want to clean the filter, we're going to get it superheated and we're going to incinerate the soot or the contaminants. And the computer needs to know the temperature. But if that exhaust is going to reach 1,000+ degrees, you need a special type of sensor, thermocouple. So we do use those on vehicles too. Right, and this is just showing like we could actually use the thermocouple to measure. Pretty fun. And then there's electrochemical. So this is going to be an overall. Don't expect to know that much about batteries right now. You're going to know the fundamentals of batteries, just how they work, from a physical standpoint. All right, so let's say that we're going to use dissimilar metals immersed in an acidic liquid called an electrolyte. In this case, let's use lead and acid. That's your most common battery. So if we go to do battery testing and battery charging later, a lot of times it'll say, what type of battery is it? Is it lead acid? And you're like, I don't know. Like pretty much all automotive batteries are lead acid unless they say they're something else. So lead acid is going to be 90-something percent. And then if you have a battery that says it's lithium ion, you heard of that? It's going to say that. If it doesn't say anything, or it says the word flooded, that's lead acid. Then we have a similar one that's very similar to lead acid, but it's not flooded with electrolyte liquid. It's absorbed into glass mats. We call that an AGM, absorbed glass mat. So let's just say we'll use lead acid, pretty normal. And see, it could be absorbed glass mat or an electrolyte, but we're going to mostly focus on a liquid electrolyte, which is why we're going to call them flooded, right? There's actual battery acid in there sloshing around. You can hear it sometimes. Don't get it on your brand new jacket. Don't ask me how I know. You'll wake up in 2 days with a hole in your jacket. Even if it's brand new and you got it for Christmas, it doesn't matter. It'll still eat the same hole in there. Okay, so remember, they don't generate voltage, but they store it in the form of chemical electricity like we were talking about. So here's a diagram. We've got positive plates coated with lead peroxide, negative plates coated with gray spongy lead. Okay, interesting. And we've got separator plates that keep them from touching, and this whole thing is going to be immersed in acid and battery, an electrolyte, so we'll call it acid. If you look at this lead acid battery, you'll see there's stacks, right? So typically a 12-volt battery will have 6, and those stacks are called cells. So if we have 6 cells, and that's all it really is, it's separations between gray spongy lead and between brown lead peroxide with a little separator in between. That's going to generate a voltage. Literally each of those cells, if it's fully charged, will generate 2.1 volts because the difference is in metals and it's immersed in acid. Now if you have 2.1 volts and you have 6 of them, what's your voltage?
12.6.
That's why 12.6 is a fully charged battery. It just has simply to do with the lead acid chemistry, that's it. Lithium batteries can be different. Lithium batteries could be like 12.9, 13, like they could be different. So our baseline, when I'm talking about a 12-volt system and 12.6 is fully charged, has all to do just with this chemical right here, right? Now, if we were to take this battery and we were to send them over here, right, we could actually make a current flow, and that current flow could either rotate a magnet or we could have, that's what's kind of interesting about electricity. If we were to use a battery to cause the current flow, it can make this magnet spin. That's like a motor. Or if we were to spin this magnet like with our hand or with wind or with the bicycle wheel or something, this magnet spinning can actually induce electricity and go either into the battery or power a bulb, right? So it goes both ways. Do you want this device to generate electricity and put it in a battery? You can do that. Or do you want the battery to put out electricity and make this magnetic thing spin? We can do that. The one that makes electricity, that's the generator. And the one that takes electricity and makes movement, that's a motor. Okay, so that's really the difference. Electricity is the important part in both of those, right? So kind of interesting. And that's what we were saying. The 12-volt battery has 6 cells, 2.1 apiece, 12.6. Cool. And then solar, just a little bit different. And so if you looked into it like physically, it's sunlight is absorbed by materials. The photons knock electrons loose from their atoms. Okay, so now we have electrons that are loose. We can do work with those. That's essentially what we're going to do. And we can make those electrons flow through the material, which will produce electricity. That's called the PV effect, photovoltaic effect. That's how solar works. So those beams of light knock electrons loose in this device, and that makes a current flow. Okay, kind of interesting. But only when light energy strikes the surface. And the amount of electrons that are knocked loose have to do with how much light is hitting it, right? So if you want to do a really cool solar system, are you going to put it under a shady tree? Its power is going to be massively reduced because you don't have a lot of light photons hitting the PV device. So you really want it out from underneath the shade, and ideally you want it at a 90-degree angle to the sunlight. So like in the summer, the sun's high, you want it like this. But in the winter, when the sun's low, you want it like that. And a lot of times we're settling for whatever the heck the roof pitch is. But if you were to really try to maximize it, you could put it on like a tracking motor that would actually change angle and follow it. You could get maximum amount of production if you could move those panels throughout the day. The problem is it takes power to move the thing that's going to move the panels. So it's sort of like you're using electricity to make more electricity. Hopefully you're winning on that. Tough to say. But that's really how the solar works. Just like that. And you know what we could do with that. Now, has anybody seen solar panels in a car? It's rare, but they're on a few. They come on like a Fisker. The old, it's Karma now, but it was Fisker Karma. They made a vehicle that actually had solar on the roof. Why do you think we don't just put solar panels on these EVs so that you never need to charge them? There is a very good reason. Most people don't know it. It's common sense, actually. You've seen solar on a house? How big is it? How are you going to put that on a car? So you could put a couple panels, and that would give you a minimal charge. If you want a substantial amount of electricity, guess what you need? More panels. So unless they figure out a way to make your solar panel much, much, much smaller and make a lot more electricity, the cars are never going to be self-powered by simple solar panels. It's just a space thing. Now, the solar panels have become more efficient, but not really like a substantial amount. Like you can get new panels that are a little bit more efficient, but not major. You would need probably enough solar panels in this whole entire room just to charge that car overnight so that you could drive it tomorrow. How are you going to do that? I don't know. Solar on top of a parking structure makes sense. You park under, you plug your car into it, the solar generates, and the solar it generates can go directly into the car. Here's the problem though. Well, if you have that at home and you go to work, your car's not at home, then when you get home it's dark and your system is no longer generating. So it'd be nice to put the generating, the parking structure with the solar at the workplace, and that's actually probably a pretty good plan, but some of you may end up really coming up with some good solutions. Electric vehicles and solar panels, to me, they make a lot of sense. Honestly, they do. But the problem with an EV is it has a limited range. And the problem with solar is it only works when it's sunny. So if you found a way to make it, and it takes a lot of space, that's probably the bigger one. If you found a way to make the solar smaller and more dense on the top of the vehicle and it can go indefinitely, I'll work for your company. You let me know. As for solar applied to your daily life, working on cars, it has nothing to do with charging EVs. It has more to do with sensors. We use these. We'll use a small solar sensor, not necessarily to generate electricity to power the car, but to generate electricity that'll indicate how sunny it is. Why do you think we care about that? Why would we care about that? All right, you got cars that turn their own lights on, turn their own lights off, right? If you jump in the car, your car needs to know if it's light out or not. Cars don't know what time it is. They just don't. So they'll put a small solar sensor in the dash, and how much light comes in the windshield will generate a voltage on that sensor, and that voltage will go to a computer, and the computer will say, oh, it's light outside. We don't have to turn the lights on. But then when it gets dark, the voltage goes down, and what do you think it's going to do? Tell the computer turn the lights on. That's it. So if you get a customer that comes in and they're like, hey, my automatic headlights don't come on when it gets dark, you may very well be troubleshooting this type of a device. So you just need to know the light generates the voltage. So if you go to test this, you're going to probably have to generate some light and see what voltage it makes, right? And that's how it works. It's not exactly magic. Now there's another interesting option. I looked at this because it works similar with this. There's what's called a piezoelectric crystal. We can put a piezoelectric crystal in a circuit where basically if there's a vibration, this sounds like science fiction, but if there's a vibration, this piezoelectric crystal will generate a voltage. Is that crazy or what? So it's essentially, you could think of it as like a vibration analyzer. The more vibration, the more voltage it makes. The less vibration, the less voltage it makes. Why do you think I pointed to this? It's a microphone. Did you know sound is nothing more than vibration? Me talking is using my lungs and voice box to generate a pressure that goes through the air that pulses your eardrum in a way that you can comprehend it. It's pretty amazing. If you really think about it, it's intense. So if we have a device that can make voltage based on vibration, the vibration of my voice box that triggers your mechanical eardrum could also generate a voltage in a microphone, give a signal to my computer, and replicate a voice, right? So this is a piezoelectric crystal. Why do you care? Well, we do have microphones in the car, but mostly that's not the example we use. We use this thing called a knock sensor. If you have a vehicle and your vehicle, let's say, you put in poor quality fuel, or you're running turbocharging and run way too much boost or something, it can actually cause knocking in the engine, mostly like fuel knock or spark, or it could actually be like rod knock too, but that's not mostly what these are for. These are more for like fine tuning your ignition timing. And if it starts to knock, this knock sensor, which is a piezoelectric crystal, an element, is going to generate a voltage, send that to your computer, and your computer's like, wait a minute, there's a knock. What should I do? Adjust the timing, change something to prevent the knock, right? So if you're diagnosing knock sensor problems, you actually have to understand this generates a voltage depending on the vibration, which is a sound, essentially. Knocking like that would generate, you'd actually be able to look at the knock sensor on the scan tool and knock on it, and you should see activity. It's pretty cool. Mice, for some reason, love to chew the wires to that thing. I think it's mostly the location. They put them down deep in the engine where stuff is cozy and warm, and the mice are like, oh, I'm moving in. They're like, ah, look at those wires. I'm going to eat those. And then it gets a check engine light, and you bring it in. You're like, oh, the mice chewed your knock sensor. Who would have guessed? And then they're like, ah. Is that covered under warranty? Like, well, it's not a defect. The warranty doesn't cover the mice. This is a ripoff. You know, I've heard it all. Right, and so that's kind of what it was saying about the knock sensor. It's pretty wild. We do a little bit additional with piezoelectric too. A lot of things go both ways, right? So if there's a vibration, it'll induce a voltage in the piezoelectric crystal, but the other way is true too. If we introduce electricity to the piezoelectric crystal, it'll make movement as well. So it can be used to detect pressure, or like in a piezoelectric injector, we'll give it electricity and the result will be that it'll move. We open and close injectors using piezoelectric crystals. Bet you didn't know that. We're literally using crystals to open and close piezoelectric injectors. They're nice because it's not real, there's not really like moving parts. You know, the piezoelectric crystal's pretty reliable. You give it voltage. Same with, if you've ever seen, like, you have some of these watches that say like quartz or something, we're actually using crystals in those watches. They're pretty good to keep time, right? If you give it battery voltage, we can get a vibration out of it, and it's good to measure seconds. Some of that stuff, I don't know all the details, but we're using these in more than just automotive, so you know. Or like in another example, let's say you wanted to measure, I'm giving you a life hack right now, all right? Don't share this information. this is totally got to be a secret. If you wanted to measure a passenger's weight, for whatever reason, all you needed to do, like someday, let's say you're married and your spouse isn't really taking care of their health and not eating right, and you're like, hey, what'd you weigh in on the scale this morning? They're like, they tell you a number and you're like, I don't think so. All you need to do is get a scan tool and go into the occupant detection system. And when they sit down, you can actually verify their weight with a scan tool, because their weight is going to change the pressure on the strain gauge, which uses a piezoelectric element, and it will give you a number. And now it might not give you a perfectly exact number, because when you sit down, all your weight may not be on your butt. Some of it might be on your feet and some of it might be on your back, right? But if you get a baseline number and then you look at it a week later after the holiday season, and you're like, whoa, that thing went up 4 pounds. It may not tell you exactly their weight, but it went up 4 pounds. So this right here, this is a truth teller right here. This system, we're using these crystals. And that is going to be in the passenger seat of like every vehicle after probably about 2006 or so. And just for your information, the reason why is because when an airbag deploys, you don't want a full strength airbag on a child. So this system measures the weight of the person in the passenger seat to determine no airbag, half strength airbag, or full strength airbag. Okay, so they're in there. And they put them in the back seat sometimes too. A lot of times. Okay, fun fact, and that's how we're doing it, all with electricity, right? And then this gets more into the magnetic fields. So, like I was saying before, we could do two things. We could use electricity going through this circuit, right? And this would be an electromagnet, and this would generate, let's say, a south pole. Do you see this north right here? Opposites attract, right? North would be drawn to south. Would you agree? But what if I flipped the current flow rather than this way? What if I flipped it the other way and now this became north? Can you see how essentially what we'll do when this is south, it'll pull north up, then we'll purposely flip it and it'll become north. And if we have a north right here and a north right here, like what's about to happen right here, those would repel. So the way we're doing motoring is we're flipping north and south poles, while this is just a magnet. The south is always going to be the south and the north is always going to be the north. You can't change those. But what we can do is on the actual coil side, we can make the north on the right or the north on the left. And right now, with the north on the left, the south will pull the north pole, then we'll flip it. The north on the right will push the north pole. That's what a motor does. So we're constantly switching the current flow of electricity, clockwise, counterclockwise, clockwise, counterclockwise, but that'll make this magnet spin clockwise. The faster we flip it, the faster it spins clockwise, clockwise, clockwise. Right? Now we could actually change its direction as well, and we could make it spin the other way around, and we'll talk about that a little bit more with motoring, but for example, your power window. You want the power window to go up, you push a button, it's going to control it where it provides the voltage in a direction, and it's going to make the window go up. Or if you push it down, it's going to reverse polarity. Provide in the other direction, it's going to push it down. But just how this is a motor, like I was saying, it's also a generator. So if we mechanically spin this thing and we rework the circuit slightly, this thing spinning can induce voltage into this coil, which can light a light bulb or go back to the battery. Makes sense? So electricity is interesting. And it's all through electromagnetism that we can make things move, or we can take moving things and have it generate electricity, okay? Motor and generator. Motor and generator are very similar. In a hybrid or EV, a lot of times we call it the motor generator. You're like, which is it? Depends. If you're trying to make the car move, it's the motor. But if you're slowing down and it's using regenerative braking, it's the generator. But it's the same part. We control the details of how this electricity flows in the electromagnetic circuit. All right, cool. And that's the main point about electromagnetism. And it works for AC and DC, but it gets a little complex. Motors are kind of its own study. There's quite a bit that goes into that. It's going to depend on the amount of current flow, the strength of the magnet, how many windings, the speed, and the distance between the field and the winding. So like the distance right here, that's going to control the power of the generator or the motor. How strong the north and south magnet is going to control the power. How many amps are flowing, right? How many windings are on here. So motors and generators, they actually get fairly complicated, truly. Mm-hmm.
I didn't understand that diagram for 2 and 4 where it has it tilted,
Yeah.
horizontal. And it makes it look like it's turning, but there's still no current. I don't fully understand that.
Well, that's okay. I can clarify, but it probably won't be everything you want to know. But let's say like right here, this is trying to show a generator first off. I like to explain it as a motor and a generator, but if this is a generator and the north is moving towards the south, that's going to generate current flow in this direction. And this was something that, like an electrical engineer would do, like Fleming's left-hand rule, I believe it's called. They could determine where the magnetic field is and which way the current flow would be. But for technicians, like we don't design them, we do diagnose them. So in this instant, while the north is moving towards the south, it's generating current flow. But right here, while the north is right next to it, that would generate nothing. So when it gets a little bit further away, it'll start generating again. See that? So it all has to do with this magnetic, we could just call it we'll call it a spinning magnet on the generator. It makes its maximum when it's like 90 degrees off of the field coil. And then it makes basically nothing when it's right next to it. And then it'll make more. And then it'll make nothing. And then it'll make more, nothing, more. And that's part of the reason that we actually wouldn't use just one magnet when we're using a generator. We're going to use multiple because their strength kind of varies. But if you were to look at this, can you see how if this strength is maximum, then when it gets up to here, it's going to be nothing? Do you guys remember on AC how it's a waveform like this? When this thing is down here at 6 o'clock, that's where it's going to be. Let's say it's at its peak low. That would be the negative, right? You remember how the waveform comes up and it gets to be like 0 volts? 0 volts would actually be right here. So this would be low, 0, high, 0, low, 0, high, 0. And that's why if we look at AC current flow, which I don't think I put up here, but if you vaguely remember, so just for everybody's, exactly, that's why AC is peak to peak like that. And so when you see AC and you're kind of like, why is it like that? It's just the way that it flows, right? AC, I believe, is like right around, no, I think I passed it. No, there it is. That's the reason that a generator makes AC. It's because that magnetic field is strongest when it's 90 degrees out, and then it's 0 when it's right next to it, then it's 90 degrees out, then it's back to 0, then it's 90 degrees out. It's just the natural production when we actually make AC current through a generator, right? And that's essentially the point that we were at when we were at this. And trust me, we'll cover a little bit more. This is just to get you introduced to electricity. It's a lot, though. Now with heating, we talked about a little bit. Let's say we use, for example, the rear window defroster. Your cars have those, mostly. Not all of them do, actually. But if you wanted, let's say for people who are back east right now, they just got hammered. Like most of the whole country just got totally wrecked. Where I'm from, they got 2 feet of snow. My brother's sending me pictures. And they think it's kind of fun when you get snow, but then the low, like I think in 2 days is -3. I'm like, I'm out. I'm commuting to work on my motorcycle. I'm done with that life. I'm not going back. You can't even make me. Even though I can appreciate some of it, no, I'm done. I'm not dealing with that. If the temperature has no degrees in it, nope, that's impossible. If the temperature has negative degrees, that I'm absolutely not going to -3. However, let's say that the back window's frosted over and I need to defog it or defrost it. That's actually legally required in some of those states. This has to work. If this doesn't work, you actually would fail inspection. You wouldn't be able to get a registration. That back window, first off, this device is not designed to melt 24 inches of snow off of it. But if you generally clear the snow off and then you run the car and you turn this on, right, your windshield's different because you got the heater blowing on the windshield, but way in the back, you don't have a lot of hot air back there. You may need this, and they have actual, we'll say loosely resistors, but really what it is, it's a coil of wire that does tend to go up and down like this, or it'll go straight, but the length of that wire is a resistor because it's a long wire. And the material they use, so if over here we have 12 volts on the left, we're slowly dropping our voltage. By the time we get over here on the ground, what do you think we should have? Let's say even just generically, we'll probably have about no volts on the other side. We start out with 12, we end with 0. As it goes across this resistor, if it's got resistance, remember it's consuming voltage. And what's the byproduct? Well, it's giving off heat, right? That's what resistors do. They consume voltage and they give off heat as a result, right? Because energy is not created nor destroyed. So we had 12 volts of potential. We end up with 0. We lost 12 volts of energy. Where did it go? It left in heat. So this will heat across the glass, and that's just a way of generating heat. It's just a long drawn out resistor, and it will actually heat the glass and melt the little bit of frost, not necessarily the 2 feet of snow. But you know what's kind of crazy? Here where we're at, it's hot, right? Window tint's nice, am I right? You like that? All right, if you tint the back window on a car with a rear defroster, and then for whatever reason there's bubbles in it and you go to scrape it off, you probably will scrape off this resistor grid. And then next thing you know, it won't work. And you'll be like, whoa, what's up? And you go back there and look. What's kind of cool is you can literally press your meter lead up against the grid. You can literally see the little lines in the glass. You can push your meter lead up against it. You should start with about 12. You should end with about 0. What should you have in the middle? About 6, right? And you can check these. And if you find one, it's like 12, 12, 12, 12, 0. The open in the grid is right between the 12 and the 0. It should never drop from 12 to 0 unless it's a full open, which means it's cut, which means somebody probably scraped it with a razor blade removing window tint or something. So if you were to do this, you should go like 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. That's a heater grid. So we're making heat with electricity because of the resistor, just the way it works. Okay, kind of fun. And then negative of overheated terminals. So if resistance makes heat, what if you found a terminal? I just actually saw this on an ASE yesterday. The concept, right? I don't know the words, but ASE L3 is for hybrid EV. There's a question about a 3-phase cable is overheated and discolored. What could be the cause? Keep that in mind. All right, in this case, what if we had a loose cable right here? Wouldn't that add resistance to our circuit? And if there's resistance right there, but the current is still able to flow, what's the byproduct of that resistance? What did the resistance make over here? So what would the resistance make at this bad connection? Yeah, and it would overheat the cable. And so that question was funny because L3 is the advanced hybrid and electric vehicles one. If you got L3, people were like, what? You got L3? The concept of that question came right off electrical basics, right off of there. It's literally an overheated terminal. How did it get overheated? Heat, which means it's got excessive resistance. And the actual answer was more close to like the terminal wasn't properly torqued. So if you didn't torque your battery terminal, it can actually get hot right there. Okay, so you know that's the effect of resistor. That's what it's kind of saying. Right here it could be kind of hot. You'll lose voltage right here. This will be resistance. Your bulb will be dim. Not only will the bulb be dim, you probably got actual heat where there's the resistance unwanted. And that's true for one of our earlier lessons. If you had a wire that was too small for the level of current flow, or the length is really long, or rust or corrosion are there, that's actually going to make heat, right? And so that was one of our main concerns is, a resistance makes heat. We do that to use a heater grid to defog or defrost the rear window. But unintentionally, if you added this light bar, it was really cool, but you used a wire that was too small, or you bought a 100-foot wire and you only needed 6, and you just like threw a big old coil of wire in the trunk, and you had all that electricity going round and round in 100 feet. That's going to make heat too, right? So let's just say it's too small and it gets too hot, that could result in fire. Cool. So it's okay to put a wire that's too large in diameter, but you can't put a wire that's too small in diameter because it's too small for the current flow and it'll make heat. And that's why we fuse it, but for whatever reason, your wire was only good for 12 amps, like a 14 gauge, but you put in a 15 amp fuse, the wire itself is going to be the resistance, and the wire itself is going to get hot and potentially burn and cause a fire, which is really scary. Okay, so pretty much, I think overall we're probably good on a lot of that. And then this gets more into like some of the chemical effects, which I feel like generally is, it's good to know. It has to do with the lead acid battery generally. So one thing you'll know about the lead acid battery, when we're charging that battery, you'll notice it talks a lot about hydrogen is deposited, oxygen is deposited. Hydrogen and oxygen are great, except for one thing. Hydrogen is flammable. So like the hydrogen bomb, or like there's a blimp, the hydrogen blimp that catches on fire. So the Hindenburg. Just so everybody knows, when you're charging a battery and it's off-gassing hydrogen and oxygen, that would mean that you have to be very careful of sparks, okay? If you have hydrogen and oxygen and it's kind of in this mix right above and around the battery, a little cloud of it, what you don't want to do is spark the battery right there, okay? So one of the lessons I'm going to give you is, if we're charging, or technically even if we're not charging and you just know that you're going to disconnect the battery or even jump the battery, first thing is we're going to deal with the negative first when we're disconnecting it, and we're going to put the negative on last. That has more to do with your wrench. If you go ahead and you put a wrench on the negative, and let's just say you touch the wrench from the negative to the chassis, it's negative of the terminal to negative of the chassis. Who cares? It's negative and negative, no problem. But let's just say you're going to disconnect the battery and you go to the positive first. It's because you like the positive better. Because it says plus, and plus is better. You put your wrench on the positive and you touch your metal wrench to the chassis ground. What have you just done? Bingo. You made a short. And so is there a fuse in your wrench? No. So that means a maximum amount of electrons are going to flow through your wrench until your wrench gets hot enough to slow them down, which means your wrench is going to be glowing, which means essentially you're welding now. That's fun, welding. Bzz, bzz, bzz. And the wrench will look like you welded, and it'll be splattered. It'll literally look like there were many micro explosions and lightning and stuff. And that's true. So when we're working on a battery, we really deal with the negative first, mostly because we don't want the wrench touching chassis if it's on the positive. But there's a whole nother side of it which has to do with this. When possible, you want to make your spark away from the battery, because there could be a cloud of hydrogen oxygen, right? Which can be flammable if it's the exact right mix. And this is pretty rare, so don't be terrified of batteries, but I've never seen a battery explode, but I know people who have. So it's one of those things, like you might not ever see it, but someone you know probably will see it, okay? If we're going to, let's say, jump a battery, if we can connect the positive to the battery and then take the negative and connect it over here on the block or on the frame, the last connection you make is always the one that sparks, and that's because you're taking a fully charged battery with a lot of potential and connecting it to a discharged battery. And remember how the electrons are going to try to like neutralize, they're going to try to even themselves out, all that talk about static discharging, right? So if there's a voltage potential in the batteries, the last connection is where the electrons can start flowing, and they may get a little excited when you go to almost attach it. When you get close, they may be like, yeah, like we're at 0 volts and that thing's at 12. You may actually have electrons jump and ship. right? So just when you're about to connect it, you might notice a little spark. You seen that when you jump a car? You hear a little zap, you hear a little something. That's not enough voltage to shock you, by the way, but the little spark, you could feel heat, but it's not actually going into your body. It's just the heat. So ideally, if we can make that last connection away from the battery, it's safer for this hydrogen oxygen. Okay, cool? So make the last connection on the frame somewhere separate from the battery if you can. And then when you disconnect them, if they've both been running a bit, there's probably gonna be no spark now because they're about equal. But if you disconnect them early, you should disconnect it away from the battery when possible too. It's very standard for technicians though. We're just gonna yank the negative terminal off, and like we do that every day. It might actually be technically better to disconnect it from the frame separate from the battery. I acknowledge. But we don't really normally do that. And while it makes sense in theory, it's like in practical application, you could disconnect batteries your whole entire career, probably not gonna have an issue. So just be aware though. And then additionally, who's ever used a jumper pack, like a jump box? Oh yeah, you have, and you're going to. With our jump box, don't be tripping because you're gonna connect the jump box up while it's powered off. There's gonna be no spark. Then you're gonna turn the switch, click, and if anything, there may be a minor tiny arc or something inside, but that's separate from the battery, so that's good. Jump boxes in a way are safer. Or if you have a really smart one, you'll hook it up, you'll push the button, and it won't even turn on until it sees everything is right. But if it's an old school jump pack with no on-off switch, that's basically like jumping it. The last connection is gonna spark, so ideally do it away from the battery. Pretty simple. Cool. And then, like with bulbs, you know how we make a light bulb glow, right? We send current, electrons go through that filament, which is a resistor. It gets hot and it makes visible light because it's hot. What about with this thing, a light emitting diode? It's a little bit different. We don't get this hot. This doesn't glow because of excessive resistance. This is different. This is a solid state device. And so remember when we were looking at those NTC and PTC resistors and all that solid state type of things, or the PNP and NPN, this is solid state. So if we have electrons flow through a diode, they'll go one way but not the other way. And a lot of times they have to have a specified amount of voltage to start pushing through. This is just a solid state reaction inside. It's not the same as a glowing filament, right? These are very, very efficient. They use very little electricity, and that's the reason why LEDs are more used in households. Saves energy, it lasts longer, it's whatever. LEDs is a better, more efficient way to make light. Just understand it's a little bit different. So if you don't know how to do the fundamentals of electricity and you had a blown taillight bulb, you could probably do what my dad would do. Pull the taillight bulb, hold it up to the light, like that, and look to see if the filament's blown. How would you know if it's blown? You see like an open in there, right? So that's how you know it's an open. Boom. It's blown, it's an open, it's etc. You can't do that with LEDs. And that's why we really want to narrow this down is back in the day you could look, you could observe if a bulb was blown. Now, you looking at this LED, there's nothing to see. Hold it up to the light, you're not going to see anything. It doesn't have a filament. Inside it's actually got some solid state circuitry, and a lot of times they'll have like a little heat sink because they do make heat. You have to test these. You can't look at them and tell if they're good or bad. You have to physically measure it. Your meter most likely has a diode test. It's a good way to test it. You could also test the voltage drop on this. You won't be able to test resistance on this. Your resistance test on your meter doesn't put out enough voltage typically to push through a diode. Okay, to test an actual LED, you have to do a voltage test or you can do a diode test. And the voltage test, again, is better, right? Because it's a semiconductor. Remember how we said PNP and NPN? It's a PN. It's a positive, negative junction, microscopic stuff. Headlights, everything. We use it all over. And then this just talks about, when we get into motors, just loosely understand, if current flow is going, in this example, to the right, it's going to generate magnetic flux in this direction. If current flow is going to the left, it's going to reverse directions, right? So the magnetic field can be changed depending on which way the current flows. And that's when they get into like Fleming's left-hand rule, I believe it's called. So for us, you know, like sometimes they'll put a lot of emphasis on which way is the motor going to turn. If the current's going this way, it's going to go that way. Or if the current's going that way, the motor's going to turn this way, right? That way would be this way. Actually, technically, I'm doing it with the wrong hand. So that's not super critical, but just understand if the current flow is going one way, it's going to turn the motor one way. But if you switch it, it's going to turn it the other way. The reason that's very important for you is when we start diagnosing things like windshield or power window motors, a lot of times it uses the same switch, the same wires, the same motor, but it sends 12 volts on the left and ground on the right, or it'll send 12 volts on the right and ground on the left, and that'll make it go the other way. But we don't have to use different wires. It's not a different motor. We just switch, and that's called reversing continuity. Okay, so when we diagnose that, when we get into wire diagrams, you'll remember that point. Okay. And then this is just more saying like when you have a conductor wrapped around an iron core, it increases the strength of magnetic field and it makes it stronger. So that's kind of interesting. The best example I got about that you could visualize is, you know, the power door locks? Old school ones that have the little thing that pops up. Like here's your door panel, it goes thunk, thunk, thunk. I don't know if like when you were a kid, maybe you were playing these games, but it was really fun to lock and unlock the doors over and over and just watch it go up. That's the easiest way for me to explain this. If you had that power window lock, let's make it this, right? And you had a coil of wire that went around it. If we send current through the coil of wire, it can actually create a magnetic field. And if you want it to be stronger, just wrap the wire around it more times. And if you send current down through this wire like this, it's going to go thunk. Then that would be unlock, right? How would you lock it? Flip the continuity, and that's going to send current the other way around it. And if it's going around this way, it's going to pull it down. Thunk. And then if you want it to go up, around this way. Thunk. Thunk. Right? So that's really all we're doing with this electromagnetism is we're going to run it around a coil of wire. And if, depending on which way the continuity is, it's going to make it go up or down. Cool? Makes sense? That's electromagnetism. And then another example would be like a typical fuel injector or the starter motor. So a fuel injector has to open and close. We'll pulse electricity and that'll make it open. And then if we take electricity away, there's a spring to make it close. So we're using a lot of electromagnetism. Remember how I said the coil of wire has to make the iron core move? You can measure the resistance of the coil of wire, and we call that the winding. So if you think the coil of wire inside, the winding is bad, you can measure the resistance of it. That's good. You can measure the voltage. It should be 12 in and 0 out. You know, these types of things. That's fairly simple. The starter uses it in two ways. You know, the starter has to turn. That's the magnetism. But the starter also has to jump out and engage the flywheel. So a lot of times we're using this coil like this. Sometimes they'll call it the pull-in coil to actually make it jump out and engage it. It's still really electromagnetism. So that's always going to be the coil of wire like this wrapped around there, like we were talking about with that coil way back here. It's very, very common use. I know it's back there somewhere. Remember, I don't think I missed it. Right here. This is that electromagnetism coil. So if we wrap around here, it can make this go up and down. Okay, you're going to see a ton of that. And with that, I think I think there might be one more page. Yeah, there is. And it just has to do with relays. So one of the things we're going to get into quick is relays. And you'll be like, how's that relay really work? That relay is going to use that coil of wire and an iron core. And when we send current through the relay, it's going to make a magnet, right? You learn that in the theory. When we send that current around that coil, it magnetizes and it's going to try to move something. In a relay, it actually moves a contactor over. It closes the relay. So on the electromagnetic side, we're just generating the magnetic field. And then on the other side of the relay, we're opening or we're closing a switch. So when we cover relays, just remember, it's still going to be electromagnetism. And with that, that was my goal. It's a lot of stuff. How do you guys feel? Pretty wiped out? You knew it was going to be intense. But it's just the way it is.